Assalamu alaikum warahmatullahi ta'ala wabarakatuh, ladies and gentlemen. Welcome back to another live stream. Let's go. Okay, let me share the live stream with my Discord server. Please join my Discord server so you can get notified and vote for next live streams, pretty much. Okay, hold on a second. Okay, hold on. Okay. Announcements. Alright, just gonna notify people about the live stream real quick. Okay, let's go. Let's go. Right, I think let's go. If anyone have joined, please let me know if everything is fine with the live stream. Like, is the quality great? Is the microphone good enough? And the video? Mic UX desktop. Okay, lovely. I think everything is fine. So let's get started. So today I'm not exactly sure what we're gonna go with first. I think I'm gonna go with maybe Swapchain recreation, so we can have we can be able to resize the window, hopefully. We'll see how that goes. If it doesn't work, we're just gonna skip it, but we'll see. Anyway, so basically what we gotta do, we gotta recreate the Swapchain. And we gotta basically recreate the semaphore, not the semaphore, no, the image views of the Swapchain, and then we should be able to basically just run the application and get and be able to actually resize the window and without actually crashing the whole application because of error out of date KHR. As you can see, it's actually crashing because of this. Let's go to the line where it's crashing exactly. Hold on, result main RS. So yeah, it's, hold on, what? 391. Let's go to 391. Okay, 91. Swapchain extension QPresent, I guess. Yeah, pretty much seems like QPresent is what it's actually interesting. On success, return whether the Swapchain is suboptimal for the surface. Okay, makes sense, I guess. Makes sense. Okay, let's go. So basically in this QPresent, we have to check if the Swapchain is suboptimal, essentially, or out of date, but especially out of date, basically. So what we gotta do, we gotta basically switch on this or match it. So let's go ahead and do this, and basically let's see. So let's remove this in wrap first of all, and let's match on this guy and see if it's okay or error, basically. So match on this, and let's go, and basically add remaining patterns. Let's go. So if it's okay, I think we're gonna get if it's suboptimal, I think. Basically it's a bool, isn't it? Huh, what? Device queues. Seems like it doesn't. Weird. But anyways, error. Otherwise, we're gonna basically get an error, and we can just check what is that error. So if error, or we could actually match on the error, honestly too. Let's match on the error, and if it's let's see, add remaining patterns. Okay, what is this? error result. Well, what about just saying error equal to vk, I guess, result? Is it? Yeah. And then let's check for out of date. Error out of date case R. So if that's the case, the predicate expression has necessary parentheses. Okay. So if that's the case, if it's error out of date, we gotta recreate the swap chain. So we're basically gonna have a variable here, mutual variable, should recreate swap chain is equal to false first, or I mean, let's go with true. Let's go with true. I'll show you why in a second. But basically, when we get that out of date, what we need to do is to essentially go ahead and say should recreate swap chain is equal to true, basically. Otherwise, we actually have some other error. In used variable should, did you mean to capture by reference instead? What? In used variable should recreate swap chain. Else we basically got a crash though. Else, I guess, panic. Or yeah, I'll panic for now, I think. Oops. Okay. I'm not sure why it's weird. Anyways, so that's something. Now why this suboptimal, it's telling me that it's not right. Can I, well, can I just this print line? Oops, I could probably just say print line and say it's suboptimal. And let's see what's happening there. What it's gonna say. So no, we. Anyways, let's just ignore that. Pretty much. I don't know what's that. Seems like a unit, basically a void kind of. Anyways, so if that's the case, we're gonna recreate the swap chain. And now, let's see. So I think before everything going on here, we need to say if should recreate a swap chain, then we essentially want to create it. So the predicate expression has a necessary what? Oh yeah, I bet. Remove parentheses. So if that's the case, we're gonna actually recreate the swap chain. Where it is? Where's the swap chain? Swap chain, swap chain. There you go. So this first of all needs to become an option maybe, or instead we could basically use std swap chain null, I think. So these are two options that we could use or go with. So I think let's try swap chain null first of all, basically. So let's go ahead and say just vk swap chain, I think. Oops, that's actually probably hash. Swap chain null? What? Swap chain null. More actions. Oh yeah, it's inside ash extensions khr, I guess. Let's find it. Khr swap chain maybe. Can I say null? Oh, I'm confused right now. There you go. I don't know why it didn't actually pop up before. But anyways, so first the swap chain would be null. And then if we create swap chain is equal to true, then we're gonna basically go ahead and recreate it. So where's that guy? Should recreate Swapchain. Come on, there you go. So here we're gonna actually go ahead and try to recreate it. So Swapchain is basically equal to that guy. Though I think Swapchain needs to be mutable, so make Swapchain mutable. Let's go. Right now I just made it mutable. Cool. And then it's basically gonna go ahead. It's gonna get the physical device surface capabilities. Yeah, pretty much. And it's gonna go ahead and create the recreate the Swapchain. Okay. Did I miss anything other than that here? It seems all good, honestly. Okay, great. Other than that, we're gonna basically go ahead and recreate the image views too. So for the image views, this one, well, I think it could be just like an empty vector at first, right? I think so, yeah. Let's just make an empty vector at first, and then when we recreate, we could like fill it up. Instead of, you know, having a option of a vector, which is very redundant. So let's just say, I guess, vic new. I guess maybe it's something like this. Yeah, it's vic image view. Is it like that or like this? No, it's actually, hold on. It's basically like, I think. Maybe like this. There you go. There you go. That's how you do it. The other thing, I'm gonna take this guy, which creates Swapchain image views, and I'm gonna hopefully put it here after creating the Swapchain, I think. So it'll be in wrap though. Hey, what are you working on right now? Hello, El Zafro. Welcome to the live stream. Welcome. So I'm not sure what I'd like to do exactly in this particular stream, but for now we're working on recreating the Swapchain so we can be able to like resize the window, pretty much. After that, I'm probably gonna look into using like creating vertex buffer and index buffer instead of just embedding the vertex data into the shader itself. And if we still have time, then we're gonna look into how we can implement MSAA, like multi-sampling, so the geometry looks much smoother. And if we even have even more time left, we could probably look into making a camera and using Glam for matrices, you know, like projection, well, not project, yeah, projection matrix and stuff like that. But we'll see. It depends on the time pretty much. But yeah, I think that's pretty much what we're gonna try to do. Of course, a lot of these things I haven't really done before, so if you don't know, it's like these streams are just like me trying to create stuff and like learn Vulkan, but at the same time just sharing with people my experience essentially. Okay, so that's pretty much it, and hopefully someone that is more knowledgeable than me is also present in the live stream so we can even help us make this work even better. Anyways, so what's going on here? Expected Swapchain KHR but found, yeah, there's no need for a semicolon there. Okay, so this should work. Actually, this should give us a Swapchain. Ahmed Norozi, welcome to the live stream. Hello. Are you coming from Discord though? Are you Ahmed from Discord or some other Ahmed? But let me know. In wrap. Okay. Yep. All right. Nice. Welcome to the live stream. Okay. Necessary and save block. Let's go. No need for this and save block. Seems like. And let's remove that guy. Okay. So this should hopefully. Okay. I also don't need this in save block here. Okay. Great. So this should hopefully recreate the Swapchain. Now let's try to recreate the Swapchain image views, basically. So how are we gonna do that? Well, Swapchain is equal to this dot inwrap. Okay, great. But this is kind of weird. Hold on. Swapchain. Okay, it's fine. It's fine. Okay, what's next? What's next? We're gonna right now try to recreate the Swapchain image views. Let's go ahead and do that. It's right here. Okay. So how we're going to do it? Well, where is the code that we had? There you go. There you go. Okay, great. So Swapchain images. So Swapchain image views. I just copied this code from what we had before. And what's going on here? Let's make it mutable. And maybe that's it. Maybe. Okay, and save. What's happening here too? Okay, we don't need in save block anymore. Okay, what else? Is there anything else that we have to do? Not really. Seems all good. Though I'm gonna do one thing. Instead of every time recreating the vector, which is not the best, I'll try to actually instead just append to it. How are we gonna do that? Well, map image. So basically we got an iterator here. So what we could do, we could go through all the iterators and essentially maybe append it. For each. Okay, let's go for each maybe. Oops. For each item, or basically image, we're gonna go ahead and we're gonna say Swapchain image views dot append. Is it append or what? Yeah, append seems like. Oh no, it's probably something else. I use a lot of languages. Append seems like it's getting another vector, appending another vector, but that's not exactly what I want here. What is it called? Maybe add, or not really. How do you even append? Oh yeah, push. It's called in Rust. Okay, great. Image view. Okay, what's happening here? Alright, I think that's pretty much it, though I'd like to make sure to clear the Swapchain image views if there's anything already there. So let's go ahead and say, I guess, clear maybe. Yep, clears the vector, removing all values, has no effect on the allocated capacity of the vector, and basically keeps the capacity, which is good. Great, that's what we want. Now, hopefully that's pretty much it. Yeah, I mean, seems all good to me. Map images. Oh, actually, the Swapchain images, that should also be recreated. Where it is? Hold on. Let's look for Swapchain images. Well, it's not recreated, but basically we need to get it again from the Swapchain. There you go. We just have to actually take this guy and put it somewhere else. Swapchain null. Okay, great. Get Swapchain images. Okay, let's just copy this guy right here, and let's go. This would be mutable. We're gonna do a similar thing essentially. So let's go to that image views. Let's go. There we go. Okay, so basically what we're gonna do, we're gonna say that. So what this would give us, this I guess would give us, yeah, it would give us a new vector, so that's fine. We cannot really do that as we have done with the Swapchain image views. Let's say images is equal to that. Basically, we're creating a new vector because, well, we're getting other elements. Anyways, so what's happening here? Yeah, let me unwrap the result so we can get our actual result. And yeah, that's hopefully should be it, really. I mean, let's find out. I guess if there's any problem, hopefully it would tell us. Okay. Alright, what's going on now? There's some exception. Encountered an address access violation, reading location. Amazing. Okay, reading location. Okay, I'm missing on something here, interestingly. It's coming from get Swapchain images. Yeah, seems like interesting. Swapchain images. Okay, it's coming from here. Read into initialized vector. Yep, right around here. Oh, I see why now. Well, this swapchain is null right here, so this shouldn't happen really here. We don't have a swapchain here yet. So let's actually just make this vector, basically, an empty vector. And yeah. Let's try resize. And there you go, it works just fine now. Well, actually, maybe not. It's for some reason irresponsive, I guess. Well, it's fine, but why cannot move it? Interesting. Well, yeah, seems good. But I can't resize it. Interesting. Hold on. What happens if I said true here? Okay. I also need to check the validation layers. So that's some. There you go. So we could actually go ahead, resize it, and seems to be all good. I thought it was more complicated than this, but yeah. But especially since we're using dynamic rendering, we didn't even have to like recreate frame buffers and all that crazy stuff. So this is lovely. Okay, what's next? What's next? Let me check, by the way, the validation layers. So let me run the Vulkan configurator and enable validation. And let's check, make sure that we're not doing anything crazy. So yeah, that seems all good. I mean, we didn't get any validation errors, so that's great. What about the API dump? Just making sure it works. Yep, seems all great. Lovely. Okay, let's go to the next guy. Let's go to the next thing, which is I'd like to also do in-flight fences, like in-flight frames, which would improve performance. But the problem with that, it's gonna kind of slow us down, because right now after that you're gonna have to handle like multiple resources for each frame and stuff. So I'm just gonna keep that for later on. So I think right now what we're gonna do, we're gonna go ahead and try to create buffers. Now this is one of the parts that I'm kind of afraid of, but let's see, let's try to figure it out. So of course I'm not gonna do the Vulkan validation, Vulkan allocations myself. It's pointless. Someone else have already done that for me in a better way. So it's called GPU allocator crate, which I actually shown in the first live stream. Hold on. There you go. But I removed because we didn't need it at that point. So now let's just get it back, basically. So let's add it back and let's use it. GPU allocator 0.23.0. Lovely. So let's go to their documentation, and also honestly, let's just compile this first of all. Okay, great. How can I check? There you go, build. So it's building it right now, I guess. Well, build script evaluation. Yep, there you go, cargo finished. Okay, let's go right now to the documentation of GPU allocator. There you go, you just create an allocator right here. So let's go ahead and do that. I'd like to use bind list later on, but for now we're just gonna stick to the old way of descriptor sets and stuff like that, because seems like descriptor bindless is kind of not that easy. So yeah, let's just go ahead and do this. Device q an allocator. So you basically need this import, and make sure to import the Vulkan one, not the DirectX 12, because this allocator also supports DirectX 12. And yeah, what else? This guy right here, same thing. Or in fact, what we could also do basically is just to go ahead and say, where is that thing? Yeah, just say this basically, and now this should all work out. Lovely. So let's actually unwrap this, and basically we're passing the instance, the device, the physical device, and here we even have debug settings, which would be interesting to see what settings are available there. What's this? This is allocator debug. Okay, makes sense. Let's see what we got here. Is there like a builder? Doesn't seem like. Okay, let's check which fields there is. So there is log memory information, which you can use to actually log information about the various heaps the current device has on startup. Log leaks on shutdown, that's nice. Store stack traces to debug leaks or other memory. Okay, that's very interesting. Log out every allocation that's been made. Log freeze and log stack traces. Hello, Yo-Yo Man 3D. Welcome back to the live stream. Okay, so for now, let's just keep it that we have such options. The other one is the buffer device address. Now, I really want to use this later on, but for now, it's a little bit more complicated to me, so we're just going to go with the normal way of doing it. But later on, we're going to try to actually use a buffer device address. Ideally, check the buffer address. Okay, never mind. Okay, that's good. So, allocation sizes, what's this? I'm not sure. Let's see. Doesn't really have documentation, isn't it? Allocation sizes. The sizes of the memory blocks that the allocator will create, useful for tuning the allocator to your application's needs. For example, most games will be fine with the default values. But example, an app might want to use small block sizes to reduce the amount of memory used, clamped between 4 megabytes and 256, and rounds up to the nearest multiple. Okay, so that's basically it's like tuning in between memory and performance, I think. So for example, games, you probably want to go on the high side for performance. What do you use the buffer device address for? El Zafro. It would basically makes our lives much easier when it comes to Vulkan, because we don't have to like manage all sorts of descriptor sets and stuff. It just makes everything much harder and makes everything less robust, and much harder to manage. So basically, it would be very easy to add like other resources and stuff without having to go crazy about descriptor sets and stuff like that. Basically, what it does. So instead of having to deal with descriptor sets, we could just like pass to the GPU or the shaders, the index of the resources that we want, and then the shader could go ahead and it's just like a pointer, essentially. It's like instead of having to create a descriptor set for a buffer, it's like you just pass a pointer to the GPU and then you just index itself from the buffer, I think. Hopefully I kind of get it, but well, I still don't understand it very well, but that's basically the gist of it. But either way, we really should use this at the end of the day, but for now we're just gonna go with the old way because that's the only thing that we have a good tutorial for. And then hopefully later on we could try it out. Oh, seems very interesting. I've been dealing with descriptor sets recently and it's painful. Yeah, it's very, very painful. So it's also, makes it very hard to create like a good engine without going crazy. Anyways, let's go. Variable allocator. So right now we have created the allocator. Lovely. Let's go right now let's go right now with the allocation. So this crate would help us create good allocations, so instead of having to do it ourselves, but we still have to create buffers and images and etc, etc. It just like, yeah, it's basically an allocator. It manages the memories and the memory buffers stuff. But anyways, so let's actually grab this guy. There's no need for cleanup. Bind memory to the buffer. Okay, let's just copy this and let's go here and let's see what we got. So basically here we're creating a buffer of size 12. Now this would actually depends on how much vertices we want. So okay, storage buffer. I don't want a storage buffer, I want a buffer. So let's go ahead and the buffer here, we're creating the Vulkan buffer. We're giving it this info. Well, honestly, you could just put it in here. It's much easier to follow the logic because you know that struct is basically for creating the buffer. Love it. And what else? Allocation callbacks, of course, none as always. Requirements, we're getting the memory requirements for the buffer. Great. Allocator, allocate. Okay, name. This is basically for debugging purposes. And in fact, honestly, coming to talk about debugging, let's look for RenderDoc already. It would help us debug stuff and have more intuition over what's really happening behind the scenes on every frame. So yeah, this is also a very interesting resource to check out. It's actually being used by, you could tell, experts of Vulkan, kind of, to actually debug what's going wrong, but we could also use it as beginners to actually learn more about what's happening right there. You're gonna see in a second what I mean. So that's gonna be interesting. Typical well, just go with complete, why not? Install, and let's go. Installing RenderDoc. Have anyone used RenderDoc before here? Okay, so I'm just gonna, okay, yes, copy new, there you go. I have finished already. Lovely. So let's check this out. What is it called? RenderDoc. Okay, great. Okay, so great. Now we need to basically give it the executable path. Okay, or we could actually like attach it to a running instance. So for example, we could actually length shift from here. Hold on, it's actually compiling. What is it called? GPU allocator. Okay, there. Oh, well, we still have this stuff. Hold on. So I'm just gonna comment this out for a second so I can show you RenderDoc real quick. Okay, run. And there you go. We got our application running. So what we could do, we could say file, attach to running instance. What? It doesn't actually. Why it only gives me localhost? Weird. File. Open capture. Window. I don't know how that works, but there is an easy way to do this. We could just take the path of the executable. Let's go ahead and say open in Explorer. Let's go. Could attack a Vulkan. I guess target. Debug. Maybe there you go. This is the executable. So you could just say Control-Shift-C, copy as path. And we could go here, executable path, there you go. We should also set the working directory. I'm gonna set it to, well, 222. We don't need, I think, this guy. So we're gonna set that to the, basically to the root of the directory of our project, which is basically called the Taco Vulkan. So as to make sure that the path is right for assets and stuff, code Taco Vulkan. Now command line arguments, we don't need any command line arguments. Okay, allow full screen, allow vsync, verify buffer access. Okay, lovely. Let's launch this. Allow access. And Where you have gone? What? Lunch? Oh, why it just shut this down? Interesting. Allow full screen, allow VSync. Very weird, doesn't seem to work out for some reason. Allow. Oh, thread panicked for some reason. Hold on. On an error value error out of device memory. Out of device memory in main.rs 308. 308. What? Okay, let's check why this error is happening. 308. It's happening here. For some reason. What? In wrap. Why would it happen here? I don't get this. Well. Minimum image count. I mean, it's working for me, isn't it? Yeah. Works perfectly for me, but for some reason in RenderDoc it actually does that. What if I don't allow full screen, for example? Blanche. Okay, what about allow VSync? What? Super confused. Okay, what about Q family indices, minimum image count? I don't know. RenderDoc doesn't seem to be working for whatever reason. Not my problem, I guess. But there is something that I gotta make sure, honestly, which is about the Swapchain size. So where I'm actually specifying the size of the Swapchain though. Weird. Window size, begin rendering. Oh, hold on a second. Did I actually, yeah, I'm not actually, hold on. I think I forgot about something though that I didn't do yet, which is dynamic state. So the viewport dynamic state should be on. Otherwise I'd have to actually create a pipeline. So let's actually add that. Dynamic states, okay. From ref, I think. Well, I guess I need to, hold on. VK dynamic state, let me check it out. Viewport. From raw. Pipeline viewport state create info. Let me go back to the tutorial real quick, because I forgot about something and that may have been a problem. I don't even know how it actually worked. So let's go to the Vulkan tutorial real quick. And let's go back to the part where they're creating the pipeline. So drawing graphics pipeline basics, no fixed functions, I think. Yep, there you go. Dynamic states, let's go. So what we need is bk pipeline dynamic state create info. Dynamic state create info. Dynamic states dot size, which is basically vk dynamic state viewport. Okay, interesting. So here we're actually having that, and we basically need two. Okay, lovely. So let's give it a slice, and let's say vk dynamic states. Okay, let's go. And now let's say viewport. We want the viewport to be dynamic, and we also want the scissor to be dynamic. Honestly, I don't even know why I didn't do both in one, because, well, if you make the viewport, well, I mean, yeah, you may want to make the scissor only dynamic but the viewport not, but, well, anyways. So there you go. So we have added viewport and scissor, and right now, since we did that, we don't need to add this viewport state here. We actually have to do it every time, every frame. Viewports from ref, height, scissors. Okay, great. Remove this from here, I think. There you go. And what else? Now let's go back to the frame stuff. Create, Swapchain, acquire next image, begin command buffer, begin. Okay, begin rendering. Do we actually give it the viewport and stuff here? Well, let's check this out. Hold on. Okay, console. Rasterizer discard enable is vacay false, but viewport state is equal to null. Okay, so I actually have to provide it with viewport state, although it's dynamic. Interesting. So let's do that anyway. And let's see what's gonna happen now. Okay, we have some other errors. Let's see. So yeah, I need to use a vacay cmd set viewport. Let's go. Let's go. Begin rendering. So before that, let's set the viewport, I think, or actually here, yeah, device.cmd set viewport, and let's say command buffer first viewport. Well, it's 0, right? And then viewports is from ref, vacay viewport, I think. There you go. And builder dot width. Okay, we're gonna go with the window size, so I guess, and dot height. Gonna go with the window size dot height, and of course as U32, or actually as F32, and as F32, I think. Okay, we need to pass in here a reference instead, basically, and yeah, that's it for the viewport. Next up is probably the scissor. cmd set scissor to be command buffer, same thing, 0 from ref. Okay, vacay scissor. Rec2d, it's rec2d. Builder dot extend vacay extend 2d. And then width is like window size dot width, and finally height is window size dot height. We need to build this builder. Okay, and let's see, expected rec2d. Oh, it's actually not expecting. Give it a reference then. In rec2d, hold on. So expected rec2d here, found rec2d builder. Oh yeah, here, reference. And that should work, I guess. Let's see. There you go. Right now it's actually working properly. Let's go. I don't know why it didn't give me a validation error that I'm not actually you know, like configuring the viewports and stuff. But there you go. Right now it actually works as expected. Lovely. Let's see if that was really the problem when it comes to RenderDoc though. No, RenderDoc have some stupid problem. I have no idea. It's panicked error out of device memory. Just doesn't make any sense. Out of device memory. 312. 312. Current extent. FIFO. Clipped surface. I don't really see what could go wrong here. Pre-transform image. Well, unless if it's like maybe image size, but not really here. Maybe I'm not setting something that it is expecting. Where's image extent, by the way? Oh, interesting. Where's the image? Oh, I think I'm not actually giving it image extent. What? Is this correct? No, I actually given it that. Okay. Well, maybe then, maybe that image extent is somehow wrong. Okay, let me see. So if let me just print this guy, just to make sure. Oops, possible, and doesn't implement. Okay, let's do it like this. Okay, let's check this out. I think lunch. What? It didn't even print that. That's stupid. You know, never mind. I'm not gonna be using RenderDoc. It doesn't seem to be working. Okay. I can't even quit this stupid thing. Did you try to destroy the swap chain before recreating it? Oh my. Good thing. Theodore Electro Logs, welcome to the live stream. Thank you for reminding me. Completely forgot about that. And seems like I cannot actually quit from this. How to quit from this? No idea. So I'm just gonna have this guy slide around there. Anyways, let's actually make sure to destroy the swap chain. Where is it? Where is it? Where is it? The swap chain extension. Create swap chain. So basically, what we're gonna do: swap chain extension. Destroy swap chain. Okay, swap chain. Allocation callbacks. Oh, well, that's or none. And yeah, and it doesn't even matter to check if it's null, because destroy functions can take null, and in that case it wouldn't do anything. So yeah. There you go. Let's check again RenderDoc. Let's give it another chance here, because we fixed that problem. Come on, I have to actually fill in that detail again. Oh well, that's clunky. So copy path, executable path, and let's put it here too. Let's remove these, and let's go here, and let's try to launch this. Oh, okay. So actually making sure to destroy the swap chain somehow fixed it, but just running the application by itself didn't really have any problem. How? I have no idea. But there we go. We have RenderDoc running, which is amazing. Lovely. So here, as you can see, it's capturing Vulkan, and it's saying how much frames it's capturing. and also the frame count and how much milliseconds each frame takes. Currently we're having around 130 FPS. So PRT screen to capture, and we could actually print screen to capture a frame. Oops, not this. And I captured that frame. Now we could probably just go out of it now. And thank you so much, Theodore, for reminding me to actually destroy the swap chain. Lovely. Okay, there you go. We got this guy now. Color pass. Well, what's going on here? A lot of crazy stuff going on. So there's this guy, which is the first thing, and then there's this, this. So this is the whole frame stuff. So at the start, what we do, this is like the capture, I guess. So we're saying VKQ submit. Yeah, VK begin command buffer. Let's go. Color pass, or beginning the rendering, and then we're drawing 3 vertices and 1 instance in rendering, and command buffer, and then we're queuing present the swap chain image. Amazing. And you also have this guy right here, and let me show you something. Now you can see that if we zoom just enough, we can actually see the individual pixel. So that's very sharp. It's not very smooth. So this what we could actually fix this by using MSAA, which we're gonna try to do after trying the buffers. And that's one thing. The other stuff that I could show you is RGB, but this is not, I can't show you this here. Pick, show background color. Okay, lovely. You could also do this, but this is not useful here. RGBA, pipeline state. Interesting stuff. It also shows you the rasterizer state here. Interesting. FB CS mesh viewer. We don't have any meshes currently, and yeah. Okay. What else is going on here? CMD draw. Oh, it actually shows you like when every command runs. And what is these? These are EIDs. I'm not sure what's that. And let me actually do my noise filter. Okay, so you do not. All right, so not right now. You should be fine with, like, you won't hear any noise from my background. Hopefully. Okay. So that's pretty much it, I think. Well, there's also some interesting thing. I'm not sure where it was. Hold on. Tools. No. Window. It's probably somewhere here. Hold on. Errors and warnings. Timeline. The resource inspector, I think. Yeah, there you go. It also shows you like all the resources that you have. So if you click on one, you could see what its device, what its physical device, etc. Anyways, never mind. So this is fine for now. No, let's just go back to work right now. Let's go back to the to the allocations. Yeah, let's actually create the buffers right now. Let's not waste too much time. By the way, is the mic fine, or should I disable the filter? What do you think, guys? Let me know if it's better to have the filter on or off for the microphone. Currently, I have it on. I just enabled it. So, okay. Import Vulkan. Okay. Just going to import everything related to Vulkan instead of DirectX 12. And yeah, that should fix it. There you go. Okay, great. Now, what about this memory location? Let's see. Two. There you go. So, okay, let's see what we have here. What's happening here? Borrow of moved value device. Interesting. What's happening? Okay, let's actually clone this, maybe. Or why it's being moved though? Well, here. Consider cloning the value with the performance cost is acceptable. Okay, let me actually see a proper error here. Device.clone in here, but why it doesn't show me in here? What? Oh, I need to name the field. Okay, great. Makes sense. Makes sense. Okay, there you go. So we could just clone the device, and I think cloning would just like clone the actual handle, not really the device itself, so that doesn't matter. Because this is, well, basically borrowing it, so we cannot do that. Okay, what else? So now here we have the size of the buffer. Now let us actually prepare an array of vertices. So how do we do that? Well, vertices is equal to, okay, let's see how do you even an array in Rust. Let's go with what we have done here though. Yeah, so this guy's right here. Okay, let's actually copy this for a second. And let's just fill this thing. So minus 0 0.5, 0 0.5, 0.5, 0 0.5, 0 minus 0.5. And this, of course, would be if 32. Probably. And yeah, that's pretty much it. Can't I just like, seems like I cannot infer it for some reason. But I could do some trick here, I guess, which is like make sure that this is f32. Okay, so that's pretty much it for the vertices array. Now what we could do, we could say, I hope, I guess the size in bytes, right? Or isn't it? Yep, probably in bytes. And let's just say dot size. This is actually an aerator. What? No, it's not. So there is len. So we could actually use that. So len times size of, oops, you actually get the size in Rust. Size of like this. Oh, actually I could say basically cd probably mem size of vertices. Is that right? What? Interesting. Hold on. Let me see. Get the size of an array in Rust. I don't remember how do you do this. Well, the size in bytes. Oh, yeah, I see. So size of, because basically time, so you gotta, I guess, give it here maybe. Well, you actually need to give it the type. So we cannot do this here. Yeah. Well, maybe. Can't we just, well, we're not in Zig, so let's just say this. Okay, let's just say std mem size of f32 times vertices.len. I thought we are in Zig, so but we're not Zig in Rust. So just go ahead and I guess. Here you go. And this should basically be casted to device size, which is right. Or I could just say maybe vacate device size. Lovely. And then usage vertex buffer. What else? Is there anything else we could give it? There's flags, which we could check out. There's also queue family indices, share in mode 2, but those are irrelevant right now. Okay. Now this is the name of the, this is for debugging basically, for the allocation. Well, let's just say allocation. Requirements, location, memory location, CPU to GPU. To the GPU and potentially for constant buffers. So right now, we're just gonna create like a buffer, I think in host, like in a memory where it's available for host and what is it called? And device, because we do not have a staging buffer yet. So for now, we're just gonna go the easy way, I guess. Buffer are always linear. Okay, cool. No need for that. But what else there is there? CPU to GPU, GPU only, GPU to CPU, and node. Okay, just this for now. Allocation scheme, GPU allocator managed. What is else here? Dedicated buffer, interesting. So for now, GPU allocator managed. What else? Bind buffer, bind memory to the buffer. Device dot buffer dot bind buffer or memory. Buffer with the allocation dot memory with the offset. Okay. Here, what's happening? Borrow of moved value. Oh well, where we're actually using that guy again. Let's see. Let me run this and it would tell me. So this in 18, line 80. Line 80 here. Okay. So can I just clone anything here, honestly? Well, let's just do it one by one, honestly. Fine. Instance dot clone. There you go. What else? Where even was that problem? Oh yeah, it was here. So yeah, that's fine now. So I think right now we have created a buffer. Right now we have to basically map it, I think, and then essentially put data into it. Put vertex, like copy the data to it, basically. If we go here to vertex buffers, so let's see, vertex buffer input description. Well, yeah, we're gonna need this too, so hold on. We got in position and in color. I don't need in color for now. Let's just go with in position, basically. So we gotta add this here into vertex shader. So we're not gonna need this anymore, hopefully. We're gonna get it from the buffer in location 0. It's gonna be a vector 2. Well, why not go with vector 3 then? Yeah, let's just go with vector 3. And in position, put it here. Yep. And we don't need the 0 here anymore. Though it depends if you want 2D or 3D. Right now, we're just going to 3D. What else? In color, I don't need that right now. Frag color, okay. What else? Just like frag color. Oh, this is dvec. Interesting. Anyways, vertex data. So we got the vertices ready, I think. Oh, actually, they're vector 2s. Right? Yeah, they're vector 2s. So never mind. Let's just, for now, let's just keep it as vector 2. Cares and okay. Binding descriptions. Okay. Vacate vertex input binding description. I think this is in the pipeline basically. So if we go to the pipeline, where it is pipeline, it's either in pipeline layout or in pipeline or even both. Vacate pipeline cache on pipeline. Okay, let's see here. It's basically maybe in pipeline vertex input. Well, let's see. Let's see actually where they put it. Vertex input binding description. Attribute description. Pipeline vertex input. It's basically inside of vertex input info. I would guess here maybe. Yeah, pretty much. Pretty much. So we need the attribute descriptions and the binding descriptions. Yep. So what we're gonna need here, basically both. So let's go ahead and do that. So vertex attribute descriptions. Let's do that, I guess. So this would need a slice. Well, let's just go with from ref. And what we're gonna do here, vacay, well, a reference to vacay vertex input attribute description builder. And let's see, so we're gonna need the format. And well, what kind of format I need to hit here? Interesting. Binding this format R32, G32, B32, S float. Huh? R. Oh yeah, I see what they're doing here. G32, B. We have Victor 2, so why that? Weird. Anyways, B2, S float. Offset of vertex, color. I think the offset for now is going to be 0. And then the binding is also 0. The location though would be 1. Okay. Okay, what else? Vertex attribute descriptions from ref. And go ahead and say vertex input binding description builder. Here we need the binding, probably just 0. And what else? We're also gonna need the input rate and the stride. So for the input rate, it's gonna be vertex input rate, vertex, I think, isn't it? What they have done here. Attribute descriptions. They're not giving it anything. What? Oh, it gets attribute descriptions, okay. Binding 0, location 1, format. Yeah, they're not giving that, which I think this is 0. Yeah, so there it's basically set up as 0 as default there. Okay, what else? Let's go with the binding would be 0 too. And then also this one I think would be like the maybe the vertex size, is it? Where's the stride? Yep, exactly, size of vertex. And how I'm gonna do that for now, well, I don't have a vertex class yet. So for now, I'm just gonna hard code it. I'm gonna say it's basically, where's my, yeah, it's gonna be like 2 times 2 size of, okay, size of F32. What's happening? Oh yeah, that's the stride, I think. And now add safe cast to 32. And I think that's basically it, maybe, for that one. Yeah. Although I need to make sure. Huh. Hold on. Stride. Move to the next data entry after each vertex, after each instance. Input rate. Vertex. Oh, there you go. Format. Oh, it's actually RG to, I see. Well, that makes sense because we only have a vector 2. So let's go ahead here. Let's B2. And that should do the trick, I think. Okay, what's next? So we got this working now. This pipeline vertex input. What is next? The vertex buffer creation. So we don't need all of this currently. We've already done it. And some things we use the library for, like all this memory allocation stuff. We have already done it using the library. Fill in the vertex buffer. Now this is what we actually need. We need to map the memory. Map memory device, vertex buffer memory, vertex elect buffer info size. Okay, let's try to do this. In where we're creating the buffer. Allocation. So this is like the vertex buffer allocation. And this is like vertex buffer. And let's just make sure to fix it. Let's go. What's happening here? Call to an MSAA function. Okay. So now what? Yeah, let's actually go ahead right now and say device dot map memory. We need the device memory, which is basically vertex buffer allocation dot memory, I think. Let's make it safe. Okay, let's unwrap this, I guess. Oh, I need the allocation actually. Dot memory. There you go. Next, device size, the offset. I also need to get that in the vertex buffer allocation dot offset. And then the size, which is gonna be basically vertex buffer. I think vertex buffer allocation to size. There you go. And finally, memory map flags. Can we actually get that here too? Maybe memory properties dot flags. Oh, actually, maybe we don't even need that. But hold on a second. Yeah, maybe in fact we don't even need this. Because I remember it actually gives me already a vertex buffer dot map. Well, not allocation, I think. Dot mapped. Yeah, there you go. Mapped PTR, mapped slice, mapped slice mutable. Try as mapped slab. Okay, so this would actually go ahead and return a valid map pointer if the memory is host visible. Otherwise, it will return none. Pointer is already points to the exact memory region of the sub-allocation, so no offset needs to be applied. Interesting. Well, that's the pointer. I don't need that. Let's go with the map slice. So, okay, this would actually give me the exact map slice I need. Lovely. The slice already references the exact memory region of the allocation. Well, I actually need mutable because I'm gonna mutate it, so I can basically put the data there. Okay, let's do this. Let's call it slice for now, and let's say dot context dot unwrap context. And let's just do this. Cannot borrow a mutable local variable, make it please, and I think that's it for that one. Now we gotta basically fill it up. Now the problem is that this slice that we're gonna get is U32, but the vertices are 32-bit per each. So the easiest way to actually do this, I think, if I remember, is bytemuck. Bytemuck. Okay, bytemuck. Of course, you could actually do this manually, but why bother? So let's see. Versions, there you go. I guess there you go. Now I added bytemuck, and let's just reload this so we can get it. Okay, great. Now let's actually try bytemuck. What happened? What? Oh yeah, this is actually should be vertex buffer. Okay, vertices, vertex buffer. Okay, so we got this here. There you go. Okay, now let's actually see how we could actually do that. Let's see. Byte mug allocation checked. Bytes off. This probably also should be maybe pod or something. Well, actually, no, we do not have a struct, I think. So, anyways. I think it was cast. Right. Probably cast. Let's see. So dot context dot cast. I think. Is that right? Well, how do I get access to it? I think it's in bytemuck, yeah. Okay, let's go ahead and do this. Bytemuck cast slice. Well, maybe it should be actually mutable though. But let's just take this down here. And here I could basically tell it exactly I want the slice to be. Though let's make use of mutable here. Okay, great. Now let's actually tell it I want it to be mutable U32. Actually 2, but yeah, F32. I think. Argyle slice is never used. Okay, nice. Okay, so I think this should work out now. So pretty much what I gotta do is to somehow copy the data. So bitwise copies a value. How do you actually copy a slice? From raw parts, from ref, in slice plot, line to chunks is immutable. Okay, yeah, copy from slice. Let's go. Copies all elements from SRC into self using a memcopy. The length of SRC must be the same as, okay. So copy from slice and vertices. Okay. And this should hopefully do the trick. And of course this needs a slice. All right, I think this should hopefully work out. Okay, let's try this out, I guess. Well, we still have to do some other stuff. Yeah, my bad. But I mean this exact portion. Length 6 does not match destination slice length 8. Interesting. So while the vertices is 6, The other one is 8 for some reason. Well, that's interesting. Why? Why? So size vertices.len. Okay. Time stdmem size of if32 as vacate device size. So why it's not the same size? Requirements. This is weird. If 32. We have something wrong here, I think. Buffer memory requirements. Mm-hmm. It's in device size. Hold on. Go to the create buffer function. Let me see. Okay, vertices 0 times vertices dot size. So the first field is structured size, which specifies the size of the buffer in bytes. Calculating the byte size of the vertex data is straightforward size of. But why it's 8? Weird. Memory requirements not size. This is ridiculous. Vertices.len. Oh, hold on. Requirements. I really don't get this. Like, why? It should be 6, but it's 8. Why? No idea. I mean, well, let me make sure that this is correct, I guess. Just to make sure. Or even let's just do it manually. So we have like 6 elements. And we basically want 4 bytes because F32 is 4 bytes. So 6 times 4, which is I think 24. Oh, yeah, 24. So let's actually do that instead. 4 bytes here. And okay, buffer memory requirements. Where else we are actually defining that size? Offset. Yeah, okay, what about this? Okay, what's happening here? Again, Slice length 6 does not match destination slice length 8. Alright, what if we do 20 here? What? Why didn't it didn't change? Really? It's still 8? What? I'm very confused right now. This doesn't make any sense whatsoever. Or maybe it's like some sort of alignment issue. No idea. Let's try that real quick. Interesting. It seems to be aligned to like 4, 8, etc. for some reason, which is weird. But yeah, let's just keep it. And what's happening here now? What? There we go. Okay, I have a little idea though. Just to make sure. So slice, copy from slice vertices. Now instead of doing this, honestly, I'm gonna say, well, no, not this, but basically this take, I think, up to, well, 6, and let's try that out. So basically I'm only gonna copy 6 there. Okay, well, that at least runs, but I don't know if that's correct way to do it. Okay, so now let's just go onwards. So I think there's probably some sort of padding at the end because of memory constraints or like device constraints or something. But anyway, for now we just have this, and we'll see if that would work out for us. Okay, nice. What else? What else? What else? What else? So right now we probably have filled the vertex buffer, I think. Can we, by the way, in map this? Oops. No, just like. Okay, never mind. Binding the vertex buffer. So let's actually bind it now. So cmd bind. Okay. Let's go ahead to draw. And before binding the pipeline, maybe let's bind the buffer. I hope this actually works. Fix buffers, command buffer. First binding, buffers, well, from ref, you only have one buffer, which is a vertex buffer. What else? We have also offsets. We only have one offset probably because we have a buffer. And honestly, not sure what offset they're talking about there exactly. Is it like the offset in the like crazy stuff? Let me just say I just say 0 now. So maybe like the actual vertex buffer offset. We'll see. So yeah. So I think that's pretty much it for that one. Now let's try this out, I guess. Okay, stop it. And let's see what's happening here. Okay, we still have some other stuff to do. Oh well. But again, you should see the what? Bruh. That's it? No way. Bind point graphics. Bind vertex buffers. Vertices dot size. What? Bind buffer memory. Oh. Yeah, we already done that stuff. So yeah, that should actually work out, but let's see what's happening here. So Wiki creates graphics pipeline. Vertex shader consumes input at location 0, but not provided. The Vulkan spec states that the pipeline is being created with Vertex input state, and Vertex input state is not dynamic, then all variables with the input storage class declared with location in the Vertex must contain a location in Wiki Vertex in oops. At location 1 not consumed by oh okay, hold on. I think I know what's happening here. What if I said 1 here? Okay, so it actually works. Let's go. Nice. I thought it would be much harder, honestly. I thought I would need the descriptor sets now, but seems like for the vertex buffer at least you don't. It's just like baked into the pipeline. Interesting. Uh, that's much easier. But I gotta make sure one little thing. I'm not sure if this offset is it in the vertex buffer itself or is it like in the allocation? Because if it's in the allocation, then we need to give it the offset of the memory, not 0. Let me check it out. Is a pointer to an array of buffer offsets. I would guess in the buffer, not the memory. To an array of buffer offsets. Yep, pretty much. So yeah, that should be 0. But basically, if I want to only render, let's say 2 vertices, then I would say 1, for example, here to skip the first. Anyways, so other than that, we also have this vertex count, which we could actually go ahead and set to vertices.len, for example. Of course, given that you want to render the whole, all of them. As U32 instance count, I could show you that later on. But yeah, that's pretty much it for that one. Yeah, let's go. We have added vertex buffers. Lovely. Is there any message like validation message? No, there's no validation message, which is awesome. Okay, so let's add also an index buffer now. And let's go ahead and do that. Well, where is the index buffer now? Let's go back here. So memory allocation, there you go. Next, staging buffer. Seems like they're trying to first of all go with the staging buffer. Interesting. Introduction. So this is basically staging buffer, which basically we could use a staging buffer to basically give the vertex buffer into GPU memory instead of host memory or host visible memory, which is much faster. But I think I'd like to use an index buffer first, then do that maybe. But it seems easy enough, I think. So, what about the index buffer now? Vector, create buffer, map memory, bind vertex. Yeah, I think that's pretty easy. Yeah, let's go with the index buffer first, then let's try the staging thing. Okay, great. Let's go back to where we create the buffer. Where is it? There you go. So right now, basically what we gotta do, get buffer memory requirements. Well, this is like Vertex buffer. Oops. Memory requirements. Okay. What kind of need to, well, what's happening here? What? Add missing fields. What? Oh, I see. I see. So this should be requirements. Not this anymore. Okay, what else? What else? What else? What else? Bind memory to the buffer. So yeah, I think we're basically gonna need to like go ahead and essentially do this whole thing. Hold on, copy, paste. Later on, we'd like to make it into a function, but for now, I think this is fine. Okay. So this would be the index buffer. Let's go. And of course, we gotta need an indices here. So let's indices is equal to 0, I think, 1, 2. The indices, but is it like in 32 or 64 or what? Probably 32, so let's leave that. And what else? Vertex buffer, index buffer, duplicated code. Okay, here instead of vertex buffer, let's say index buffer. There you go. And what else? This is gonna be an index for debugging purpose. Here, allocation scheme, bind memory to the buffer, rate. Couldn't get a mapped slice. Okay, now instead of, oh my bad, hold on. So index buffer. Let's grab this and let's use it. Vertex. There you go. And also this should be called index buffer. Oh my god. Come on. Index buffer allocation. Here too. Index. And here. Index buffer. And basically, where is index buffer allocation? There you go. So this, and yeah, I think that's it. Though this would be 3. And other than that, where's the size? Is this correct? No, it's correct, but not completely correct. Because U32 and F32 is the same size, but let's just make sure to do the same thing there. Okay, what else? What else? What else? Did I miss anything? Next buffer allocation 0 up to 3. Well, honestly, instead of hard coding this, we could just say vertices.len, you know. Here, vertex.len. Other than this, the same thing here, indices.len. And of course, to the vertices, this is going to be indices. So we could copy from it. And what's happening here? Oh yeah, I need to also here. And that's pretty cool. Okay. Yeah, that's pretty much it, I think. Bind buffer memory. Okay, great. And now let's go ahead down into where we're drawing and stuff. And we gotta use another command. So instead of cmd draw, well, do we need to bind the the thing first. Yeah, we need to bind it. So let's actually do that first. So device.cmd bind index buffer command buffer, and then the index buffer. Let's go, and the hold on, I think let's go. So for the offset index type, I think I'm gonna go with 0, isn't it? And index type, what's that? Oh yeah, you actually tell it which type you want to use, I think. Interesting. You could tell it you int 16 or you int 32 or that other stuff. Currently we're using you int 32. That depends. So this should be good enough, I guess. Good thing to use 16 water anyways. Let's just use that one. And what else now? I think this is good to go for that. Other than this, we're gonna go with, interestingly enough, you could actually bind one index buffer at a time, seems like. But for vertex buffers, you could actually do multiple. Weird, I don't know why. Anyway, so other than that, instead of cmd draw, we need index draw. Draw index. And here we need the command buffer. X count, well, it's indices.len as u32. Other than that, we need the instance count. Instance, we're not using multi-instancing. Default vertex index at 0. And yeah, and then the first instance is also 0. Basically, that's an offset. So I think that's pretty much it. Now let's just remove this. And if everything were correct, then we should be using an index buffer now. Let's go. Seems all good. Now we're using an index buffer and a vertex buffer, which is amazing. So let's try to create a quad, for example, just to make sure this is perfectly correct. Correct. Okay. So here we have our vertices now, indices. And by the way, instead of doing it this way, let's use Glam. Let's add a mathematical library, which is called Glam, I think. We'll see how it goes. If this would work for us or no. We'll see. Okay, let's see. Versions 0. Okay. Let's add this to the mix. And let's go here. And now, instead of doing this, we're gonna have like vectors instead. So let's see how we could do this. Well, honestly, first of all, I'd like to have a struct called Vertex. Struct Vertex, and add bytemark that crazy stuff. And for that, before we could do that, probably I need to add a feature to bytemark. So version is equal to this. If I remember, it's called derive, I think. Maybe derive. There is bytemark, derive, and derive. I'm not sure. Let me check. Bytemark, derive. Where is bytemark? Okay. Where's the features? Features. Yeah, pod. I want this. Where is this? You don't need a feature or what? What? Zeroable. Weird. Where is the features? There you go. It's core only by default. What? Okay, let me do something. If I get my terminal I could say cargo add bytemuck. Pretend that I'm adding bytemuck, and I'm gonna get this. So by default, it seems like it's already adding these. Let me go step by step. Maybe let's remove this for now, and let's just try it out. Okay, hold on. What I'm doing? No. Let's try it out now and see what feature it adds. Yeah, it doesn't add derive by default. Okay, I'm not sure which feature is good here. What is going on here? Yeah, it's actually changed that stupid thing. Features is equal to, I guess, derive, but we'll see. Okay. So what's happening here? Yeah, I need to do this, I think, and derive byte muck. Yeah, what's happening? Basically, what's pod derive pod. There you go. Okay, let's see. Show recursive implement trait, add derive attribute. So it doesn't seem like it's seeing it. Okay. What about bytemuck derive instead? But let's see this one first. Hold on. Okay. See that got any? No. Okay, let's try bytemuck derive then. Sure, there is few features. Not that stupid. But anyways. There you go. So it's basically bytemuck derive, not derive. Okay, let's go ahead and add that now. Bruh. Bytemuck. This is super confusing. Bro, what? I'm confused. Or maybe we need both? No idea. What? Oh. Go down. Repr C. Repr transparent. How can I add it? Repr C. Basically, to make sure it's compatible with C API, essentially, and pod, and probably also bytemuck zeroable, I think. Bruh. Yeah, fine. Let's import these, honestly. Come on, come on, come on, come on. Writer is super slow. Now let me sure. Hold on. Why this is stealing result? There you go. Super slow. Anyways, let's just remove this and see what's gonna happen now. It's not implemented for trade. So yeah, it just needs the derive, seems like. Anyway, that's super crazy. Okay, so the X and the Y. Well, basically we need Glam Vic2, I think. Did we add the Glam already or not? We did. So what's stopping it? Okay, let's go to Glam. Vectors, Vic2. Oh, I see. So position is equal to Vic Glam Vic2, I guess. There you go. We'll just import this anyways. Import. Okay. The trait bound is not satisfied. Okay. Now what's happening? Is not satisfied. The trait bound pod is not implemented for Vic2. What? Maybe we don't actually need it. I have no idea. Anyway, let's just see. Just see what's gonna happen there. Okay, repr C, copy and clone. Do we even need these? No. Anyway, let's remove this one. So that's the vertex. It's basically position. Have only one attribute, position. Cool. So let's see what we're gonna do now. Q allocator vertices. Okay, so here. So instead of an array of these guys, we're just gonna say like vertex. But honestly, I'd like to. Yeah, it's fine. It's fine. Then we could just say vec. Not sure how you create it. Oh, what? Oh yeah, I see. And now again, vertex. Well, basically, I'm gonna copy this. Here. There you go. And say same thing here. Yo. What? There you go. Okay, nice. So now we have 3 vertices there. Nice. Okay, what's next? Now vertices.len. So now instead of this, what we could say times vertex, basically. Cool. Other than that, what else? Let's copy from slice vertex. Let's actually go with this here. Is not satisfied. Oh yeah, let's actually add now that copy and clone and stuff like that. Okay, let's see now. The trait bound vertex pod is not satisfied. Is not implemented for vertex. Hard for vertex implement. Oh yeah, well, we do need that to be pod, but Glam is not allowing us to actually. So yep, not allowing us for some stupid reason. Okay, let me see if Glam can help with that somehow. Byte check. Prox byte mock forecasting into slices of bytes. Maybe I need this. I don't know. Ran byte check. That's the only thing that seems maybe. Where's Glam? There you go. Now let's add features. Okay. I got it now. Is this? Okay, right now it got fixed, seems like. Amazing. So I just had to actually add bytemuck into that crate, and now it is actually good. Great. Glad I figured that out. So what's next? Where is the vertices? There you go. Create buffer, blah, 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 blah. Yeah, seems good enough, I think. So let's try this now. I mean, it should be the same exact thing, just that we have right now a nicer layout, I guess. There you go. Amazing. Lovely. Okay, amazing. So next up, we would probably need to make some other thing nicer, which is the binding stuff. Where is it? Graphics pipeline, layout. Yeah, vertex input state. Let's go. This is the one. And what we need here, let's see. Flags, push next, vertex binding descriptions, and attributes. Yeah, we could just pass this right, but there is some. Let me just see the flags real quick. There's no flags. What we can do is, yeah, we're just gonna take these guys and we're gonna put them in, well, this whole thing, I think. This whole thing. Yep, that. And we're just gonna say vertex. Okay. Like vertex, if that makes sense. And then we can come here. I'm not sure how you do static fields in vertex in that. Let me see. Rust static fields. Let's go. There you go. You can declare an associated constant in an impl. Let's go. You just impl const. There you go. Okay. So impl vertex. Okay. And, oops. Const state, basically input state equal to this. And what's happening right now? Missing the type for const. I do have to actually tell it the type. And by the way, let's build this. Don't know why my ID is slow, which is also slowing me down. Uh, yeah, this should be VK. And let's go finally. So that's how you do it. Now let's check that out if it worked. Input state. Okay, so that's pretty much it for that one. Okay, so what we should do next right now, I think we have basically, ooh, what? Oh, well, that's interesting. So seems like it cannot really uh, call functions, I guess. Hmm. So, well, I could actually do it without the builder. I think that may help. So const input state, vk pipeline, vertex input state creative. Now this is nasty looking, but I gotta do all sorts of crazy stuff like s type, for example. But anyways. Or maybe I could just say it here, pipeline vertex state create info structure type. Why it's not giving me anything? Then this is, oh, why? What the? There you go. The other thing that I want to set, well, in fact, I gotta set them all now. So this gotta be like, I guess, null. Flags, 0. Well, not really 0. Vacate pipeline, vertex, input state creates flags. Come on. There you go. Empty. Vertex binding description count 1. Vertex binding descriptions. Ooh. That's gotta be, well, that's interesting. So no, here's, well, I think I got an easy way to do this actually. It's pretty easy in fact. Let's remove constant and create a function. Call it input. I think this would work. Yeah, I think this would work. Input state. Is this enough? Let's see. So we're actually doing that. There you go. So now instead of that, how can I make a function static though? Found. Is that how it goes? Oh, I'm not returning it. But if I remove this, no, let's get it back. Okay, so this should hopefully work now. Yeah, seems like. Oh, no, it doesn't. Interesting, why? I mean, it's the exact same thing. The Vulkan spec states for every binding by each element, the value of the binding. What? I mean, I'm doing it here, so what's up with that? Finding 0 is an invalid value. What? And by the way, I don't think I need this as location 1. But maybe it's invalid. Hold on. If I go back to Vertex, input, state, maybe, let's try this instead. I don't know, but let's see. Let's just make sure that's not a problem. No, it's not. Ridiculous. Very weird. Okay. What if I look into the old ones? main.rs and let's check for, okay, let's check for here vertex. Well, let's check for example binding. What? Oh, we didn't have, I see. So okay, what if we go back now? No, I cannot. Very weird. Vertex attribute descriptions. Yeah, it's somehow invalid. It's like it's giving it 96. Yeah, it's probably filled with garbage. But I'm not sure why that is the case. Rust struct static function. Okay, let me make sure. Let me make sure one thing. Where I'm using that input state again. Okay, let's just see if this is really. Okay, let's try this. So it's inline now. Okay, so the problem is it cannot be inlined. This doesn't make any sense. Build. Oh. Okay. Build. Oh, maybe I shouldn't actually build it. Hold on. I think maybe I know now the problem why. So where I'm actually giving the create info, right? So what if I gave the builder instead and then build it in place? Is that possible? 5 times specifier. Okay. So let's just say this, I guess. This maybe. Yeah. And and let's just go down now to input state. So instead of this now, use a vertex. Let's see if this would work now. Okay, returns a value referencing data owned by the current function. I see. So yeah, I don't think this worth it, honestly. Unless if we like just use a struct instead. Yeah, pretty much. If you want to use a builder, we just have to do it in line. But well, let's try to do this. I guess I think we'll hope this one. Come on. Oh, I see. Pipeline vertex info. Basically, there was like a problem where, in fact, basically, if you don't like, if you build the builder in the wrong spot, then you basically get invalid data for temporaries, basically. So that was a problem. Okay, and I was going crazy. So yeah, let's just make it like this. So for the S type, I mean, can't I actually use default though? Yeah, really. Do wonder that work. Well, what about this? Confused. It's probably importing the wrong default value. Not sure where that's actually, bro. std default or what? No, it's not. Yeah, there you go. Okay. But I can actually go ahead and like use this. Yeah. So just like, well, it's really not helping at all. So stupid. Use default, I think. And what's happening here? Is defined multiple. Oh, okay, I see why. So, when it always ruins my imports. Okay. Where's default now? What? There you go. Okay, so hopefully that would actually fill up that stuff. Next up, I would just add vertex attribute description count, which is going to be 2. Oops, 1. And vertex attribute descriptions, which is going to be a pointer, in fact, which is nasty in Rust to use pointers. And put the attribute description. Oh, wow. Wow. Cost vertex attribute description. Okay, say let description to Vertex input binding description. Then oh well, since that actually also have well, no, it won't work. It won't work at all. Yeah. Because it's reference like pointer gets, yeah, basically, unless if we allocate it, which is just stupid. Like, why? Yeah, no, let's just not use a function, honestly. Well, unless if we do one thing, which, you know what, never mind. It's like I wasted a lot of time on this stupid problem. No, let's just inline. Why bother? Yeah. Let's go back to Vertex input says, oh my god, I wasted too much time for no reason on this guy. Don't touch it. Okay, so yeah. Yeah. Okay, great. So what else now? So we used buffers, we recreated the swap chain, and okay. Yeah, I wanted to show you something. I wonder what it was. Yeah, I wanted to show you if we can actually create, oh yeah, how we can like pass the time to the shader. And for that, I guess I'm gonna use push constants so we can do some little stuff into the shaders. Why not? Where is this pipeline? We're recreating the pipeline here. So there's also pipeline cache, which is interesting. Create infos, folder, blah blah blah. Okay. So maybe here it's push constants. Not here, it's somewhere else. I guess here. No. Where push constants was exactly. Oh yeah, I think it's pipeline layout. Where is pipeline layout? There you go. Yeah, probably. There you go. Push constants. And let's see. From ref vk push turns vk push constant range builder. And let's see what we need here. So you basically need size and offset for some reason. And stage flags. Oh. What? Okay, hold on. What else is in here? So there's push constant ranges, set layout count. Weird. Oh, yeah, in here. Just say builder dot size is equal to 4 bytes, and let's say offset, yeah, 0. And okay, is there anything else we need? There's also stage flags. I guess basically we gotta tell it like which shader stage we're gonna use this in. And can we actually tell it like multiple stages? Like what if I give you first environment? That would work. Now we basically described the layout. Now let's try to pass it up. Okay, create image view, acquire next image. Begin rendering, CND, save viewport. Okay, here. Somewhere around here. Okay, let's try. There you go. Push. And what this needs command buffer. Need pipeline layout. And stage flags. Let's try both and see if that's possible or not. Should be possible, I think, but offset. Then we give it the actual constants, which are in bytes. Okay, cool. It's a slice. Let's get the time. Like basically every frame, we're gonna get the time is equal to std time instant now dot elapsed actually not I guess seconds f32. Oops. How do I get the time that is passed? Well, okay, let's do this. Let's just say let's equal to std time in roughly and now and then what we could do, go down and here right now I could say now minus the get the elapsed as seconds f32, and then we could hopefully say from ref time. Nah, that wouldn't work. We need to turn it into bytes somehow. Okay. So cast. Let's try to do it here, I think. Problem with this, it takes cast slice. Cast ref mutable A. Okay, hold on. What about is equal to byte cast slice or cast base ref time. Then here we'll let UH, right? Interesting. What about time? I need somehow to actually turn this constant to, okay. Rust constant to slice of bytes. With a specific value. I don't think this is the case that I want here. Yeah, no. Oh, actually, hold on a second. What if I try to just to delete the bytes from it? 2B bytes. Ooh. Yeah, I could actually turn it into bytes. Interesting. But there's like this BE, which is probably Big Indian, Little Indian, and NE, which I guess native Indianese. Let's try this one, actually. Yeah, let's try this one. Yeah, it actually gives us a slide bytes. So, and then what happens if I get yo, okay. Yep, I think this should maybe work. But how do I get a push constant once again? Shader push constants. I just forgot how do you do it. There you go. Oh yeah, you say something like this. It's kind of like an SSPO or something. So push constant, uniform constants. Now here the data, basically float time, and let's see. I wonder if this would work. So no errors so far, but let's try to use it. So in position, let's say for example times sine of time. Constants. But time, I guess. There you go. Let's go. We have done it. Amazing. There you go. That's what I'm talking about. So basically right now we have actually gave the time through a constant, a push constant, to the triangle. Pretty cool. Pretty cool. I wonder if I could like also give it like the camera matrix. Though most of the time they actually gave it through uniform, like what is it called? Uniform buffer. In fact, sometimes even the time constant they give it through uniform buffer. But I'm not sure. Like, there's nothing really stopping me from using the push constants for that, although the push constants is kind of small. But anyways, so this actually works out. Amazing. But just to make this more good enough, I guess we gotta create a struct for it. So let's actually create a struct, something similar to Vertex, basically. What is gonna be called push constants. And here we have time F32. And down here. There you go. Okay. So right now we got the structs, which only have time currently. Okay, cool. So let's go down to, well, where exactly? Time. There you go, here. And here we're actually going to create the push constant. And for that, we're going to basically say, yeah, we're going to grab this guy, create a push constant slice. And we're going to say the time equal to day, and let's go. That's basically it. Next up, we would too simply have to turn it into a slice. of bytes. How are we gonna do that? Well, byte muck cast slice, not probably, and here we're just gonna give it the push constants. So that work? Expected but found. Oh, actually, no, weird. Okay, what if I said push constants dot bytes, 2 bytes or something? What? I'm confused now. Rust struct 2 bytes. What? Well, I want to use byte muck. There you go. Bytes off. Push constants. Okay, that seems to be fine. Let's go. There you go. So right now we have a struct called push constants, which we could basically pass into the shader. And then we could use it in the shader to do cool stuff like this, for example. Let me also show you, for example, let's maybe pass a camera, I think. Orthographic camera, maybe. And we could also, what we could do is also show you like some instance stuff, how instances work. But honestly, let's try to maybe do camera. Okay, let's see. We're gonna need Glam for that, but how are we gonna do that? But would that actually work? Maybe? Maybe not. Yeah, honestly, no. But we could indeed go ahead, let's see, for example, offset. Just as an example, though, later on we're gonna have to do the actual matrix stuff, probably for every single object, essentially. But for now, let me just show you using an offset here, for example, vector 2, and then what I could do, let's go to this. Oh well, there we go. And here in the push constants, we could fill it up. Let's say offset, and let's say, for example, and then here we could just do any offset we want, or like let's say an example here, and then it's basically a matter of making sure it is the same here. So here we're gonna take a vec2 offset. I don't, yeah, like the names doesn't matter as long as the layout is the same. Like this is float, this is vec2, you should be good to go. Or maybe this could be like float instead of vec2, I guess. So yeah, that's pretty much it. Though, well, yeah, I think so. Anyways, but shouldn't I actually update something though? Let me try this out anyways. So minus offset. Probably have to update something that I forgot, but let's see. Yeah, I do. I do. So probably layout. Yeah, pipeline layout, my bad. So you actually have to change the pipeline layout. Okay, vertex and fragment. By the way, those variables are actually available in vertex and fragment because of this. So, okay, let me see the pipeline layout where it is. That's, I need to basically change something there too. So here we got size and so yeah, now instead of from ref, we need to pass it a slice in fact. And how we're gonna do that? Well, let's see. So instead of from ref, and it shouldn't actually be this being built now. Okay, so that's basically the first one. Size 4, offset 0, because it's a float, essentially. CDM to go I'm talking about here. F32. Yep. And now 32 found U size 32. Let's go. So this is the first one. Now the second one would be for our new property, which is offset. For that, we're going to go with vic2, like the size of vic2. And then offset would be this, like the size of this guy, because this is what's before it or what comes before it. So size of f32. Basically, we're going to offset to the second property with that specific size. And yeah, we could also control which vertex or fragment. And yeah, that's pretty much it. This should work now. Okay, let's go, but we have some problems, seems like. Maybe it's due to alignment, maybe. Okay, duplicate stage lag sounds in ranges 0 and 1. Ooh. Okay. Oh, I see. Yeah, I think that's not how it works, really. How it works is probably, in fact, we need to tell it here, and we don't really need to here. Probably only need one. Yeah, I thought it was like the vertex binding description. Vulkan spec if I push constant block as its clarity shader, both the shader station range. What? As a push constant 0 vacay shader vertex bit has a push constant buffer block with range 0.16, which outside the pipeline large range of yeah, it's alignment, and I think it's probably due to the alignment here of push constants. So can I make it packed? How can I make it packed? I wonder how do you do that in Rust? It's probably due to alignment issue. Let's see. What? There you go. Repr packed. Default representation alignment lowered to 2. I think it's probably repr packed 0. Maybe. What about that? Oh, we cannot redo 0? Not a power of 2. So what packed? With the align and packed modifiers respectively, they alter the representation specified in the attribute. If no representation is specified, the default one is altered. Default representation alignment lowered to 2, alignment raised to 8. Lowered to 2. But why cannot? Invalid repl packed attribute. What the? Repr C. Oh, is it like 1? Maybe 1, yeah. No. That seems to be still the problem though. Why they can just tell how to do it? That's stupid. Might be what you're looking for. Is there maybe something in ByteMark that would help here? No idea. What? Oh, you could just say packed, I guess? Oh, interesting. So, okay, I guess you don't need this. So you can see pack. Is that it? Hopefully that is actually the actual problem. Damn, it's not somehow. What? Well, Vk shader state vertex bit has a push constant buffer block with range 016, which is outside the pipeline layout range of 12. 12. Oh, well. Or maybe the alignment issue is in the shader itself. I'm confused. Okay, let's try to do something here, I think. So, which outside the pipeline layout range of 12? Uh, let's see real quick. Nah, that doesn't work. Which is outside the pipeline layout range. Now it's 20. What about 8? I think it's probably the problem here. What? That doesn't change anything. Or maybe I actually need to tell it not packed, but line. Oh, well, maybe. Maybe. We'll see. Come on. Okay, what about align 8? Push constant target type without padding between tabs of different sizes. Indently size bytes. That's crazy. Well, hold on. What about Ash? Push constant? Well, there's a Vulkan tutorial here, interestingly. Let me see how they have done it. That may help. Uniform buffer object. Well, there's nothing special there. Well. Shader stage vertex. Pushing the opacity. Offset equals 64. Okay. Okay, what if I actually tell it exactly what I need here? What if I said packed, just to make sure it is indeed packed, and then maybe I could say what it was here? Layout offset. Well, float is 4 bytes, so bruh. Remember alignment 8. Oh, it can only be a multiple of, well, interesting. Well, no idea. Fact. So, no way. I have no idea how that works. There's probably some memory alignment problem, but I'm not sure how to fix it at all. Anyway, I wasted enough time on this one. So let's just remove it for now until I figured it out. So right now, I think let's go with the staging buffer. Let's create a staging buffer. Vic2 is 8-bit aligned, so there's 4 bytes between time and offset. Vic2 is 8-bit. There's how to fix it exactly. Vic2 is 8 bytes aligned, so there's 4 bytes between time and offset. So I guess we basically maybe mean, hold on. So I understand you right. Then there is 8-bit aligned, 8 byte aligned. So this is like in used, I think. Well, I think there's an easy way here, maybe. Which maybe we could just say flick to offset and then there may be like a padding here. Okay, let's try that, what we are telling here. So in Put 4 bytes of padding after time. Also update pipeline layout to have 16 bytes of push constants. Okay, that's it out, I guess. By padding, let's say F8. Oops. But U8. No, what I'm doing. Actually, let's say U22. Is it? Yeah, 4 bytes, right? Yep. What about now? Oops. Missing padding. Okay, that works. Nice, thanks. Oh my god, finally. So basically, in GLSL seems like there is padding. I think HLSL doesn't have that problem, maybe. But there you go. So as you can see, the triangle have been offsetted um, from the host, of course. But yeah, that's just was an example. So let's just remove it for now. But let's go. That works, I guess. Though it would have been nice if like there was like a better solution instead of adding fields like padding 0. So instead of having to maybe somehow to just like see line to use 4 bytes. Guess line 32. Or actually that bytes also has pretty strict alignment. Yeah, interesting. Let me see if this would work by any chance. Oh, actually maybe 8 bytes. Yeah, that doesn't work. I have no idea. Anyways, that's fine. So if you want to do that, you can just add it here. Should set the alignment to 16. Ooh. And put the offset first. Okay. No. Cannot transmute between types of different sizes. It's weird. And line 16. So anyway, never mind. Never mind. So for now, I'm just gonna keep the time. That's fine. Time. Push constants dot time. Let's remove this. Oops. Let's go. And that's good enough now. The line is correct. The other code is wrong. Well, anyway, let's not waste a lot of time here. So I think we're done with that for now. And let's go down to push constants. Offset, no need. So, but having the time. Then we could also have like the mouse coordinates, for example. And that would be nice, I guess. Mouse coordinates. But there's no need for anyway, never mind. Okay, what else other than this? Let's go ahead and try to make the, what is it called? Yeah, let's try to make the staging buffer. Introduction, blah, 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 transfer queue, instruction buffer creation. I think there's nothing new here, right? Create buffer, blah, 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 blah. Vertex buffer. Hello, Zero. Welcome to the live stream. How's it going? Memory requirements. And then you could basically give it the user properties. Okay. Vertex buffer. Using the staging buffer. Let's go. Fine, and you? I'm great, thanks. Just been battling with some alignment issues. Oh my god. Create buffer. Staging buffer memory. Transfer SRC. Host visible. Host coherent. Staging buffer. Buffer size data. Transfer SRC. Oh, there's two buffers. There's what? Oh, I see. So basically, we're creating a buffer, which is going to be the transfer source. It's going to be host visible. Basically, yeah, it's going to be host visible and host coherent. That's the staging buffer. But now the vertex buffer would be transfer destination bit. So you could basically transfer memory from the staging buffer to the vertex buffer. It's also, of course, vertex buffer bit. And then there's like vk memory property device local bit, which means that the vertex buffer right now would live in the GPU memory, in dedicated GPU memory. So yeah, and then primary allocate command buffers. And then we're basically gonna make a command to copy the buffer from the source buffer, our staging buffer probably, to our destination buffer, which is the vertex buffer, I think. Yeah, but where's the ST buffer and stuff? I don't know. Yeah, it's probably a function. Interesting, okay. Q submit, let's go. And then it's waiting, just making use of wait idle. Have you started learning development with Roblox? I actually learned Roblox I started learning Roblox like 6 years ago, and I have left it around 1 or 2 years ago. Yeah, probably 1 year ago. But yeah. So I don't work with Roblox anymore. Q submit, Q wait idle. Graphics Q. Free command buffers. Create buffer. Copy buffer. Okay, makes sense. Makes sense. Makes sense. Makes sense. So here's the deal, I think. But honestly, before that, let's actually let's commit this stuff. So if something doesn't work out, we can go back to it. So basically, by the way, what I've changed here. Yeah, we added push constants. And yeah, we added the vertex buffer. We also added the index buffer. And what else? Vertex buffer, index buffer. Yeah, we also made the Swapchain recreatable. Okay, great. So basically recreate Swapchain and vertex buffer in, well, also, well, basically Swapchain recreation, vertex buffer, and index buffers. And finally, push constants is what we have added so far. Commit. Okay, great. So we also added ByteMock and stuff like that, and Glam. Okay, and you have a job in IT, or is it your hobby? It is my hobby, but I do have a contractor job using Go.Engine currently, so that's something. But though probably soon it's going to be an official job, but who knows? We'll see. So yeah, it's a hobby, but also a job, I guess. But yeah. So my job is basically kind of like creating games in some sense in a game engine. But my hobby is pretty much mostly, well, while I also like enjoy game development, but lately I'm more into game engine development or tools development in general, and low level development in even more general. So yeah. Yeah. Like I'm not very much more like interested anymore too much on games, creating games themselves. But yeah. Like for example, creating an operating system, even creating a computer, something like that. Anyways, so that's basically it. Yeah, well, let's try to create a staging buffer now. So I think I know what I gotta do, but I never tried this, so we'll see. Okay, bind vertex buffers, set viewport. Let's go up. Okay, so instead of vertex buffer, I think what we need to do is create a staging buffer. Well, honestly, I mean, it is. Uh, so here's the deal. We're just gonna copy one of these guys. Vertex buffer, memory requirements, blah 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 blah. All of this. We're probably gonna persistently map it. Maybe, I don't know. But for now, though, let's see. Actually, do we really need to? Yeah, we do. Anyway, let's just keep this on here, and let's put it here. I do need to make this into a function, but anyway. So this is the gene buffer. I wonder what capacity, what size he gave it. Oh, create vertex buffer, create buffer, easy staging. What size? Oh, is he creating like a staging buffer for every single? What? Are you kidding me? Create buffer, okay, it's basically the same size. So here's what he's doing. He's creating a buffer with the same buffer size. Transfer SRC bit, host visible. Then he's mapping the memory and then in mapping it after mem copying. Well, interesting. And I wonder what's gonna happen like if the actual vertex buffer doesn't fit in, like if it's too big for the staging buffer. Well, I mean, like you cannot, like you do not have unlimited, like not a lot of memory capacity for staging buffers, because well there are in host visible and the host coherent memory, which is quite small. So I think maybe around 258 megabytes or something like that, but I don't know. The 256 or something like that. Depends on the device. But anyway, we're not gonna care about that now, honestly. And I think we're just gonna do something similar to what he's doing here. Just create a staging buffer maybe for each and every buffer for now, maybe. What do you think? Queue submit, create buffer. I've been developing a Roblox for 2 years and I want to move on to something more serious to get a job, but I'm lost. Well, it depends. Do you want to create games or do you want to create game engines? Or do you want to create applications? or websites. The only offers I get are web projects, which I hate. Oh, well, so what you love, like apps. Yeah, for apps, I would go with C Sharp. In fact, even if you want like for like later on to go, for example, for games like Godot engine or even Unity, although I don't recommend Unity, then or some C Sharp game engine, then you're gonna need C Sharp. But either way, for apps, pretty much I think the standard currently is C Sharp, so go with that. At least I recommend so. Go with C Sharp, learn it. And I'm not sure which library you would use, but maybe starts with WPF. Uh, it's kind of old at this point, and maybe there's like WinForms, which is the new one. But either way, just go with C Sharp and WPF if you want to develop apps. I think that's pretty much the best way. Otherwise, if you like low-level development more, you want to get control of your application even more and memory, then maybe WX widgets or Qt. WX widgets or Qt. And for WX widgets and Qt, you have to use C++. You could also use Python, but no, I don't recommend that. But yeah, if you want to use C++, go with Qt or WX widgets. If you want to use C Sharp, then probably go with WPF at least for now. Though a lot of the skills are transferable, so just go with WPF, learn that, and if you want to go to another library, you probably can easily. But pretty much like the UI knowledge is pretty transferable. Anchors, etc., whatever. Bindings, I guess, and something like that. But yeah, pretty much if you want to develop apps, someone said to me Tori. Tori is basically similar to Electron, which is I honestly wouldn't go with that one. I mean, like most apps currently actually go with Electron or Tori. Tori is actually not bad, at least it's better. But basically, let me tell you why. Electron, it's just taking the whole Chromium browser backend and just slapping it into an app. Like every app you make holds with it a whole browser, which is crazy. I don't know even how that's. Anyways, and of course it would consume a lot of memory, and it would also the application would be very big. And that's the first thing. Second thing, you would need to actually kind of like just like developing a web application, just use HTML, CSS, JavaScript, whatever, stuff like this, to develop Electron apps. So I really don't recommend Electron apps. Although if you just want something real quick that works, I guess that may work. But yeah, like personally, I wouldn't go with Electron. Tori though is similar, but another story. Tori is much better than Electron for app development, in my opinion. I think it's developed in Rust though. I don't have a lot of info about Tori, honestly. But I mean, it's at least better in terms of the fact that it also have like a browser, like your whole application also comes with a browser, I think. But at least that browser is much more lightweight. I think it's using a web. I don't remember exactly what it was, but yeah, it's using a much more lightweight browser kind of thing. And I think it's also made in Rust. So if you want to go that path, then yeah, I wouldn't recommend Electron. Go with Tori. Though honestly, I wouldn't really go with this kind of things anyway. So I just recommend going with WPF if you want some desktop app. Though if you want something cross-platform like that works on all platforms, then yeah, go with Tori. I think that would be good too. Pretty much. So it's built on Rust. There you go. Cross-platform. It works on everything because it's pretty much just a browser. Like yeah, pretty much balloon size, less than 600 kilobytes. Yeah, like if you value cross-platform and you want something simpler, I think go with Tori. Yeah, pretty much. I don't recommend Electron. Have a desktop bundler, scope file system, native not. Yeah, pretty much. I'm actually interested in Rust, but do you think it's too far removed from other languages in syntax, etc.? What do you mean removed? Like, for me at least, I learned a lot of languages. Like, I learned Rust, C, C++, C Sharp, GD script, Python, Lua, though I'm pretty much mostly, like, I have most experience with Lua because of Roblox. So at some point, it becomes very easy to learn languages. Though C++, although I learned all these languages, but C++ is another level. It's like you can never. It's like even the basic stuff is so complex. Um, so I don't recommend C++ honestly. Uh, in the long term, at least. It's like there's just a lot of holes that you can fall to. If you want to go that path, probably go with C, honestly. Unless if you really need to. But anyway, so yeah, I do recommend Rust, maybe Zig in the future, and probably C sharp if you don't like managing your memory. Yeah, pretty much C sharp if you don't like managing your memory. If you want to go AI, Python may be simpler at this point currently, though. Yeah, like so different that it's not worth to learn. What exactly? Rust? Not really. Rust is pretty good, but the problem with Rust is the borrow checker. You're gonna have a hard time with the borrow checker for someone that only knows Lua. Yeah, if you're just coming to low level languages, I'd recommend starting with C. You know, it's like don't go anywhere. Start with C or at least Zig, because there you'll have to manage memory explicitly, and you'll learn a lot pretty much about memory. Because when it comes to Rust, it won't allow you to make mistakes when it comes to memory, and it just bothered you a lot. So, but in C you can do apps. Well, I mean, if you're just starting, I don't recommend going to GUI right now. It's like you need to learn a language first, and you need to learn how to manage memory, etc., etc. Like the basics, the essentials. Because coming from Lua, you have a lot to learn before you can actually. So it starts by just creating console apps, pretty much simple console apps, learning memory, how to manage it, etc., etc. So yeah, but if you really want to, there is some choices. There's like, what is it called, JTK, but I don't recommend this. No, most people don't like this. I think. But that's something. It's cross-platform. It's actually created in C if you want to use C. There is also, what else? Not sure WX widgets if it can be used in C, though it's a C++, but there may be a binding there. I don't know. Other than that, what else? Yeah, honestly, I don't have a lot of choices when it comes to C. Yeah, there is also MGY, but this is also C++, but it does have a binding in C. But the problem with MGY, it's not like your regular traditional GUI stuff library. It's basically for immediate, which is very different. But honestly, I don't really recommend this. Just probably go with Tori. I'm not sure what Tori uses. Probably JavaScript, I guess. Not honestly sure what it uses. I mean, it's made in Rust, but like what you create your apps in. Not sure. But anyway, just honestly, if you're starting with GUI apps, I'd very much recommend C Sharp because you don't have to deal with memory, and pretty much it's the standard when it comes to desktop apps, desktop GUI apps. So yeah, that's hopefully helped you kind of get an idea of what you would like to do next. But of course, go ahead and try things and just find out if it's for you or not, basically. So yeah, variable staging buffer is never used. Okay, so The problem that I have here is that it's basically creating staging buffer for every damn buffer. So let me see, staging buffer size limit or something, I don't know. The 256 megabyte limit seems to correlate with the 256 megabytes PSI. Well, indeed, like actually using the staging buffer would take much longer when it comes at first, like but you're basically paying the cost at first. This is all about Vulkan. It's all about paying the cost up front by creating everything you need up front. That's why it takes a lot of code to just even get a triangle, because you're creating everything you need up front. Like you're creating a pipeline, you're creating render paths, you're creating blah, 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 all that crazy stuff up front. And it's a similar story with the staging buffer. What you're gonna do basically here is you're creating a buffer that is visible from the host and from the device. Like both the device and the host can use it essentially. But this buffer, the problem with it is that it's very slow to access from the GPU. So what you gotta actually do, you gotta create a buffer in dedicated memory of the GPU. For example, my GPU have a dedicated memory and it contains 4 gigabytes. 4 gigabytes. There. But also the other thing is that a staging buffer is very buffers that are visible like or can be used by the host and the device, the GPU and the CPU, I think is very small. I think. But here you go. So my GPU have like 4 gigabytes of dedicated GPU memory. This is like dedicated. It's very fast to access, very fast to write to, etc. Because it's in the GPU. Thanks for all your advice. So tomorrow then begins my day in C. I'm going to bed. It's getting late. Good night. Thanks again. Hope one day will be strong. See ya. Goodbye. And have a good night. You're welcome anytime if you want any advice. Come in. So yeah. And there's also GPU memory. So and there's also the shared GPU memory. I think this is what is used for a staging buffer, for example. But anyways, currently following using seem to be a lag. Okay, let's see what this guy has said. I have multiple pools of device memory called heaps. Well, most GPUs have multiple pools of device memory, but anyway. There's no point in staging vertex data. Textures still need staging because of tiling. Why? So device with more than one heap, first thing you need to find out are in multi-memory. The fastest possible access time for GPU operation. Let's go. But device local memory is usually not directly accessible from the CPU. Yeah, pretty much the problem with device local buffers, or the device like the buffers that are inside of like the dedicated GPU memory, is that you cannot access them from the CPU, from the host side, because well, they're not accessible. So what you gotta do is actually create an intermediate buffer called a staging buffer that is both available, or not available, but usable from the device, or accessible from the device and the host. Then you basically copy your data to that staging buffer. Then you use a command buffer to actually tell the GPU to go ahead, copy the data from that staging buffer to the actual dedicated buffer, because you do not actually have access to the dedicated buffer. Only the GPU does. So you instruct the GPU, tell the GPU to copy the data from that buffer, that staging buffer, to the device local memory. But anyway, however, that isn't maybe useful. Okay, communist. Okay. In cases where vertex data is being dynamically generated every frame to not staging. Yeah, so of course this is correct. I mean, if you're gonna be like every frame giving vertices, giving new fresh vertices, then of course you wouldn't benefit from staging buffer. That actually won't be even usable, since every time you'll have to copy from the buffer, etc., which is not going to be great. So no, if you're going to be like doing dynamic geometry, which basically changes vertices every frame, that's a no. You won't make use of a staging buffer. Uh, but in our case, and in most cases, it's the static geometry, which won't change. So a staging buffer makes sense. Okay. Also be advised that some discrete GPUs will have a special heap of around 256 megabytes. It's special because it is both CPU accessible and device local. Okay, so I think I'm getting this wrong. I see. So in fact, there is two types of CPU and GPU accessible, I think. One is probably device local, which basically exists in the device. And this one is the one that is limited. And there is another one which is also accessible from both sides, but it's probably basically the RAM. Yeah, the RAM, the host memory. And that's the one that is slow. Presumably, there's some fast channel for the CPU to write its data to device memory. Yeah, basically the PSI, I think, or PCI. This memory heap is designed for streaming usage, so it would be pretty good for your needs. So the size is adequate. The size tends to be around 256 megabyte regardless of the GPU's total memory. Okay, so right now I just need to figure out exactly what's happening here. Hold on. Staging buffer. Syntax buffer, I suppose this should be like a generic buffer. This is basically gonna be a transfer SRC because we're putting the data that we're gonna transfer from it. Another buffer. So that's the usage. I mean, you could in fact go with any usage, like I mean all the usages, but that's not good for performance reasons. You should only go with the usage flags that actually you really need. Okay, Vertex buffer, get buffer memory. Okay, let's actually get the buffer fragments here, and then this is staging. But honestly, at this point, let's create a function for this. Really, yeah, let's create a function. Because it's gonna be a while right now. So okay, let's actually copy this from here. Well, in fact, only this maybe. Yeah, pretty much. Let's try to create a function. Hopefully, let's hope the Rust burrow checker wouldn't make a problem for us here. So create buffer, and yeah, duplicated vertex buffer. Okay, so this is basically the buffer that we're creating. We need, of course, a device. And the key device. Okay. The other thing that we need is the actual size. So basically, U size, oops, size, U size. So here instead of this, you gotta do this. Size as vacate device size. Okay, the named creator buffer found for. Oh, Ash. Sorry, Ash device. Ash device, and here we need the usage flags. So that's also something we need every time. So usage. There we go. That's the usage flags. Next up. Memory requirements. Okay, this is buffer. There we go. And this is buffer memory requirements, or essential memory requirements here. And let's go ahead and do this. Well, we do need the allocator, a reference to it maybe. Hold on. Okay, let's try it out. So allocator is basically allocator. So we're gonna move it if possible. Make allocator mutable. Yeah, mutable, but basically turns mutable hopefully. Is it? There you go. And then memory requirements here. And then here we have the name of the buffer essentially. So name, device. Well, let's actually leave it at the end. Name. This is gonna be Caesar. Sorry, CR. How do you do that? There you go. That's the name. That's just for debugging. And this is of course buffer. Okay, what else? Honestly, let's create a struct. I like structs better. So buffer create info or something like that. Okay, great. So here we're gonna need like usage flags, name, size. What's happening here? Missing lifetime specifier. Oh my god, no. Well, I really don't want to go the lifetime length. But I guess, I mean, let's see. Though, hold on. The name, what this takes? Yeah. Yeah, it takes str2. Interesting. So that's it for the name. What's else? Okay, device, info, buffer, rate info. So now I could say info dot size, for the flags, and what's happening here? There you go. And here info dot name. What else? Is there anything else here? There's also key family indices, which could be useful later on. Maybe. But anyway, for now it's fine. Okay, what else? Linear, I don't care for that now. CPU to GPU. Well, this is interesting. So info, memory, location. Yeah. What else? Linear, I don't care about that now. What's this? Dedicated buffer. Dedicated. Weird. Okay, let's just say allocation scheme 2. I don't know exactly, but let's say info dot. Okay, what else? What else? What else? What else? Bind buffer memory range. And that's pretty much it though. This is the buffer allocation. Yep, I think that's it for now. For now. So let's see. Well, honestly, instead of starting with the staging buffer, let's start small. So what's happening here? Oh yeah, this guy. Cast slice mutable. This, well, let's just try it right now with this kind of vertex buffer stuff. Without the staging buffer for now. So we can test this. Okay, great. But hold on a second. Remove this mutable, okay. Hold on. So here we got the buffer, which is what we want. Memory requirements, we don't need that. Buffer allocation. Now, what about the buffer allocation? Would that get like destroyed? If that's the case, then we have a problem. Bind buffer memory. Okay, let's see. It returns allocation. Does this have a drop? I wonder. For allocator. Yeah, seems like only for allocators, so it's maybe fine. Let's see what we can get here. Memory mapped PTR. Now, honestly, this is also important. So, okay, great. So let's actually say struct buffer, I think. Then we just contain handle, which is going to be like vk buffer. It also contains the memory, which is probably vk memory. Actually, allocation, sorry. Allocation. Oops, like this. Okay, buffers is not constructed. Okay. And this would basically get at, is it like this or like this? No idea. Anyways, buffer. Okay. And here I could just say buffer and then give it the handle and the allocation. And what's happening here? Cannot find value allocation in the scope. I could just call this allocation and we're going to call this handle. That's pretty much it, I think. Function create buffer is never used. It's never constructed. And what's happening here? It's never constructed. Okay, nice. Now let's go down. And instead of this craziness here, up to binding the memory, basically. I'm going to comment this for a second. And we're basically going to say vertex buffer to create buffer. Actually, instead of create buffer like this, since we have already created the struct, why not actually put this into a constructor instead? Impl buffer. This is you, and this is self. And that's pretty much it. Okay, so now what we could do is equal to buffer, and here you need to give it like mutable reference to layers, not this, and then you need the device. And then buffer creates info. Honestly, we are not owning the device, so we could also probably go with this. Right. Let's put the reference to device. Well, okay, we need now the buffer create info. So we have size. It's going to be vertices len. SCD. What do you actually get in? Hold on. Get array byte size list. That just doesn't seem possible here. But there is a little trick that we maybe can do, which is to byte. Can't it? What? No. Really? Disease. Well, what about slice? Taking a slice. Let's just say vertices.len comes vector called vertices. Well, in fact, say SCD mem size of. What is the type of the vertices? Vertex, yeah. That's the vertex. Oh, yeah. Like this. It's happening, okay. Now usage flags. Basically, probably vacate above usage flags. This is a vertex buffer. The name will be all vertex format. Memory location. And known GPU only, CPU to GPU, GPU to CPU, or CPU to GPU. Okay. To GPU for now. And the allocation scheme is managed. Allocation scheme managed. There you go. What else? What else? What else? What else? Vertex buffer allocation. So right now what I could say here is, instead of that, I could just make some function to copy from or to make use of this. Let's grab that and let's come here to the buffer and let's fn copy. I guess copy from, and let's go ahead and cast slice middle. And basically we're gonna say self. Well, of course we need self first. So self, I guess like this. Oh, it's probably like this actually. Maybe this, yeah. The allocation. Let's go. Make it usable. And what else going on here? Yeah, we need either buffer or result. Okay, so let's say anyhow result buffer. Sorry. Well, in fact, it's gonna give nothing, isn't it? Does this give any error by any chance? Well, doesn't seem like. So what we could do, in fact, this guy, what? Oh, it's actually an option. Well, that's interesting. But anyway, let's just, I guess, say anyhow results. So we could say this now, okay. Yeah, there you go. And now vertices all So basically here you need to get the slice that you're gonna copy from, which is in this case gonna be well, slice copy from slice. Hello, DGK123, welcome to live stream and wa alaikum assalam. So slice, copy from slice. Oh, actually in this case it's vertex. I see what's happening here. Oh yeah, makes sense. So let's actually maybe add some sort of template. I don't even remember how do you do templates in Rust. Thank you, DG. Keep it up. Thanks, thank you so much. Slice. Maybe slice of T. Would that work? And then T here. What else? It needs to be a pod. Okay. So where T is pod. Does that work? There you go. Great. What else? T copy from slice. Okay, great. So this should help. Copy from makes sense. Okay, now let's go ahead here where we were. Okay, here basically. And let's say, so after creating the vertex buffer, we're going to say vertex buffer copy from, and we give it the slice here, which is our vertices. By itself, seems like, well, it's not maybe. Type mismatch. Expected but found vertex 3. Oh well, it's expecting a slice. Oh yeah, let's see. So basically I need to give it a reverse. What's happening here? Cannot borrow immutable local variable. There you go. Lovely. Much better. Nice. So just say vertex buffer copy from vertices. Nice. Amazing. Amazing. It also infers the T, which is vertex in this case. Amazing. Okay, let's go ahead for the same thing basically with index buffer. So we're going to comment this out for now. All this trash. And do this. This is an index buffer. And yeah, this is the name. And it's going to be an index buffer here. And size of not vertex, but U32 and CPU to GPU. Yeah, same thing there. That's pretty much it, I think. Vertex buffer copy from, well, index buffer copy from, instead of vertices, indices now. Well, mismatch types. Oh, I see. So vertex buffer dot buffer, or dot handle, in fact. Same thing here, because right now I have our own kind of thing. Okay, what else? What? Cannot borrow slice as mutable because it is also borrowed as mutable. Oh my god, what? What are you talking about? Set it until now. Would that work? Oh, actually, what's happening here? Weird. Oh, okay. See. This should be not slice, but mapped slice. Okay. And I guess right now it's fine. I could just say this. What about now? Amazing. Perfect. Let's go. Let's go. So yeah, we successfully have kind of abstracted the buffers. Lovely. Love it. Okay. So right now, instead of all this trash, this is how you create it. And this is how you actually copy it. Like how you fill it with data. Pretty cool. Amazing. Copy from vertices. Now, same thing here. Index buffer. Right, in fact, we can even do something pretty cool. But you know what? Never mind, there's no need. So here, index buffer. We can remove all thing. And right now the actual buffers is just this little code. Lovely. Okay, so right now we can in fact go ahead and try to make a staging buffer. So here we're just abstracting the buffers. Commit. Great. So we abstracted buffers. Now let's try to create a staging buffer. So let buffer equal to buffer mutable allocator device. I'll honestly same thing almost. And variable staging buffer is never used. Remove variable. What? Staging buffer. Okay. And yeah, this is not a vertex. This should be transfer. Amazing. And this is like and maybe also vertex. Hold on. If we actually go back into this, it's actually transfer, vertex, and all sorts of crazy stuff. Every buffer? Don't know. I don't know if it's actually possible to like just use one staging buffer for all buffers essentially. I think, but yeah. Can I say all now? It seemed like empty default. Yeah, there's no full as it is. Leave it as transfer src, and yeah, this is CPU to GPU. And next up, this vertex buffer and this index buffer, they would be not CPU to GPU, they now GPU only. So basically dedicated. I'm not sure about this GPU allocator thing. It's probably a dedicated buffer, I think. Maybe. But what's happening here? It seems like it's a function for some reason. What? Weird. Let's say GPU allocator. By G Oh, I see. So like if you want to do it yourself, seems like no need, I think. And then we don't need to copy from any, we cannot do that in the first place. And we can indeed do something pretty cool, which is to just save the memory allocation and just check out to make sure that it is possible. But anyway, there's no need. And here what we could say, index buffer, we also don't need to copy from anything. But we do need for in terms of the staging buffer. So after we create the vertex buffer, we're going to go ahead and copy from the staging buffer. We're going to copy from vertices. The size, okay, interesting. I don't know, for now I'm just going to set the staging buffer size to something big. I don't know how big that would see, 256 megabytes or something. Well, let's go with 64 megs, for example, for now. And how I'm gonna do it? Well, let's say, so this is in bytes, right? And megabytes are like, I think, million. 10 to the power of 6, I guess. Oh, this is a, let's see. Honestly, let's say, okay. Or to simply, for now, not sure if that would be great, but yeah. So that's the staging buffer. Nice. It should be as big as possible. And then for now, I think this is 64 megabyte, or at least close, unless my math is wrong. Anyway, yeah, vertex buffer. So basically, we're copying from vertices. So what's happening here? Okay. Okay, so after copying, what's going on here? Oh, yeah. Okay, so after copying from vertices, right now we basically need to tell it to copy to, basically. Copy to. So we basically need some sort of function to tell it copy to buffer. And to buffer, how are we gonna do that? Well, yeah, we're gonna tell it to copy to the vertex buffer. Of course, we're gonna give it a reference. And yeah, that's pretty much it, I think. And now we're just gonna go ahead to buffer and make that function copy to. Copy to. So fn copy to is gonna take self pretty much, and then it's gonna take some sort of buffer reference, of course. So we're gonna give us anyhow result essentially. And yeah. Okay, finally, okay. There you go. Now, okay, now what? Now we need to basically also get a command buffer. Need to create a command buffer. Interesting. So we can basically record to it the operation. Well, interesting. Now the problem if we do that is that we're gonna keep track of synchronization. Because I mean, you cannot use the command buffer at the same time because, well, here's what we could do. We could take like a command buffer, or at least a command pool. Then we could fill that. Yeah, I think maybe let's go with command pool. So, but let me see how he's done it himself. Let's see where exactly that is. Free buffer. Using the staging buffer. Okay, copy buffer, allocate. Okay, so here's what he's doing. Source buffer. How is allocating command buffers? Command pool. Where is the command pool here? Weird. But anyways, probably taking command pool from a global variable or something. I don't know. And yeah, he's allocating his own command buffer right here. And immediately start recording the command buffer. Start recording the command buffer. Okay. Then he's saying copy buffer. better usage one time submit. And then he's ending the command buffer. And then finally queue submit and queue wait idle. Queue submit and queue wait idle. Graphics queue. Okay, no handle. And then he's freeing the command buffer. Interesting. Well, we can in fact make like an abstracted queue. In fact, but for now, let's just go with the easy way. We're just gonna basically take a command pool, I think. Yeah. Buffer level primary. Begin info. Okay, let's take a command pool, I think. And also gonna need a queue. Interesting. So command pool. And we're gonna need a queue to commit. Unless maybe if we just give the command back, no, there's no need. So vk command, oh, queue, sorry, queue. And yeah, basically need command pool, the buffer to copy to, or we could call this destination buffer. And then the command pool to allocate from a command buffer, and then a queue. And basically right now we could say, yeah, we need to create first of all a command buffer. So command buffer is equal to command pool. Come on, what's happening? There you go. Allocate. Yo, what? Oh, we need the device, my bad. So we need the device, vk device. Then device dot allocate. What's happening? Oh, this should be ash device. Okay, and now this allocate command buffers. And here vk allocates info. Yeah, builder dot soloiding. Here we could give it the command pool. And we could give it the command buffer count. Is it? Yeah, only one. And then, what else? Level, yeah, command primary. Oops, command buffer. Level primary. vk results, interesting, but to not to vec, but into iter, and then get the first item, and which is basically next. Dot context couldn't allocate command buffer. And yeah, calling an save function. More actions around it and save block actually. And what else? Yeah, let's actually pass in the reference. Command pool. This needs to be cloned, I think. Don't know why it's taking it by object, but anyways. All right, so that's essentially it for the command buffer creation or allocation. Is there anything else I missed? Doesn't seem like. And now what I'm gonna do after having created a command buffer, we could actually start recording to it. Begin. Huh, what? Oh yeah, device. I always forget. Begin command buffer, then you give it the command buffer, then you give it the aka begin info. Taking years to give me. Let's go. Influx, inheritance. Yo, what you give it here? Nothing. Okay. And here you give it a reference. Is that it? Surround it and say block. Okay, and then here in wrap, I think, no, just propagate back the result. Yo, what's happening here? Can only be applied to values that implement try. Okay, let's unwrap this for now. What else? That must be used. And used result. This is very weird. Come on, why it's super slow? Okay, there you go. All right, I see. So we can just do this, I guess. And yeah, that's it for that one, I think. Now, after beginning the command buffer, let's end it. And surround and save block and expect. I mean, can't I just say this? Yeah. And same thing here. So before ending the command buffer, let's say cmd copy buffer to buffer, I think, or something like that. Yeah, copy buffer. Though what else we have? There's also copy buffer 2. What is the difference? Specification between buffer regions. Overlapping. Graphics on compute. The command must only be called outside the render pass. What is the difference? So that's command buffer 2. Okay, what about command buffer 1? Okay, let's see what is the difference. So, or the equivalent command provided by vkhr copy commands 2. So, okay, this actually takes parameters. Yeah, and this actually takes a struct, which is more coherent with the Vulkan API. But are they the same? No idea. Let's see. And let's check this guy. Yeah, pretty much seems the same, just more nicer API wise. So let's use that instead. Why not? And then let's say command buffer. And then here, vacate command buffer. Info2. Yo, copy buffer. Copy buffer info2 builder dot. And now the source buffer, which is basically self.handle. And the destination buffer would be well, destination buffer dot handle dot, and well, we also gotta give it regions. Let's see. Also, what's happening here? More actions surrounding save block. And yeah, builder. Let me see what the tutorial have done first. There you go. So what it done exactly? Let's see. SRC offset, DST offset. Ooh. Copy buffer. Oh, I see. What? Oh, copy region. I see. And what is one here? Hold on. VK, well, device, CMD, command buffer, copy buffer. And that's the, what? Oh, yeah, the count, how much regions there is. I see. So basically one region which only have the size. Amazing. I see. So let's say regions from ref because we only have one. And let's say vk buffer copy 2. Is it? No. Probably region or something. Oh, it's actually buffer copy too. But and yeah, builder. And now let's see what we got. Okay, so you have the source offset, destination offset. We don't even need those in our case. But I guess we need the size maybe? Yeah. And the size is basically the size of the destination buffer, not the source buffer, because well, the staging buffer could be as big as possible. Though, hold on. Good question, actually. I mean, we could. But anyway, for now, I just hard code it as the destination buffer size, because that's my use case currently. But we may change that. Okay, size. Well, how do you actually give the size, in fact? Is it even possible? Where's the size of the allocation? I guess, yeah, allocation size. Yeah, let's just hard code it to this now, though we could add some more customization if you want to. But anyway, for now, this is fine for my use case. And that's pretty much it, I think. Now we just gotta submit this command buffer to a queue. Device submit queue submit to, and here we gotta give it the queue that we got, and then finally submits, which is basically from ref, and then here submits. How are we gonna deal with this? Submit info to. Honestly, later on, I probably what I'm gonna do is I'm gonna have like a queue object. And then basically this copy to operation will just return the prepared command buffer. And then we'll just submit all those commands at the same time. Actually, would that even work? Not really. Yeah, no. Because if you do, then it would... no. For now, at least, no way. Okay, from... well, anyway, let's just go the simplest way right now. So from ref, submit info to builder. Okay. And command buffers, infos. Hold on, what? Yeah, command buffer infos. And here we're gonna say from ref, make a command buffer, submit info, builder dot command buffer, give it the command buffer. Let's go. Let's run this within save block. And let's just propagate back the error. This method takes 3 arguments, but 2 arguments were supplied. It also needs a fence, which we actually maybe need here. Well. Okay, let's just see the other stuff for now. Command buffer, there's device mask. Is it index or mask? Yeah, mask. Well, we'll just keep it as that for now. And then you got the command buffer, you got what else? What? That's it? Weird. And yeah, that's the command buffer infos. Let's go. And what else? There's signal semaphore infos, which we don't need. Wait semaphore infos too, which we don't need for now. So let's not get caught up with optimization, I think. Yeah. Okay, so we don't need any of these. But we do need a fence. Now the question is, do I want to create another fence or just reuse some fence? I guess let's just reuse some fence. Maybe. Yeah, let's just reuse some fence. I guess. So in resolved reference fence. So how the tutorial does it? VKQ. Oh, it just uses VKQ wait idle. I mean, that makes sense, I guess. Yeah, it's fine. So let's say just for now, fence no. Why not? And then let's just do as they do, which is wait idle here. So, well, this is not perfect for now. This should Bob, I think. So device dot queue wait idle and the queue. Oops. This. Okay. And that's basically it, I think. So we're basically beginning the command buffer. We're allocating one first. We begin in command buffer, then command copy buffers, and then the command buffer. Oh, I actually forgot one thing, which is maybe flags. Is it? Actually, maybe not. Yeah, no, this is probably in creating a command buffer. Yeah, where he said it. Command buffer begin info. Oh, okay. So yeah, it's here actually. Dot flags. There's one time submit. There you go. We're only going to use the command buffer once and wait with returning from the function until the copy operation is finished executing. It's good practice to tell the driver about our intent. Okay, and command buffers. Do we need to deallocate? Yeah, there you go. Free command buffers. Free command buffers. Okay. Like the draw commands. Schedule multiple transfers simultaneously and wait for all of them to complete instead of executing one at a time. That may give the driver more opportunities to optimize. Well, honestly, can we use a staging buffer for a texture? Yeah, I think we can. But anyway, for now, make a free command buffers. Okay, let's use that to free the command buffer. So device.free command buffers. Here we gotta give it the command pool. Let's go. And then we gotta give it the command buffers, which we only have one. Which we're basically gonna give here. Great. This is also probably unsafe, maybe. Yep, it is. So we can easily just, put it here. And here we have command pool. Oops. Oh yeah, command pool dot loan from ref command buffer, found command buffer. Okay. But this actually frees all the command buffers. I mean, it's fine. But what? How? Three command buffers. One. Oh, I see. Anyway, makes sense. Makes sense. Makes sense. So that's pretty much it. Hopefully for copy too. Man, that's a lot. Okay, physical device, Q, blah 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 blah. Now we need the command pool before all of this craziness. Where I'm creating that. Let's check where. Here, I'm creating it basically here. So let's grab this guy. Let's go up there in where are we creating copies from? Copy from slice, there you go. Okay. So somewhere around after the queue basically. So yeah. And now what we're gonna do is in copy to here. So we basically need buffer. The destination buffer, which is in this case Vertex buffer. Then we need the device. Then need the command pool. And the queue. Honestly, you know what? Let's make it simple here. Let's do this. Hold on. Copy to. Let's just device command pool queue for now. And I think we don't need this clones now. Which is useless in this case. Okay, great. Now let's go back to copy to. Yep. Give it reference. Oops. Here we need to give it a reference. And of course, finally, check if there's any error. And yeah, that's pretty much it. Now, if everything have gone right, we can also do the same thing here, but instead of vertices, we need to copy from indices. And copy to values after being moved. Interesting. Okay. Let's like this. And let's go here. Let's do this. Is that correct? I think so. Oopsies. Okay, great. Does not need to be mutable. Yeah, remove it now. Yeah. Okay, amazing. So we got a vertex buffer, we got an index buffer. Then we copy from vertices, copy to vertex buffer, copy from indices, copy to index buffer. And that should do the trick, I think. I think. Though, honestly, we should have probably done the fins. Well, anyway, for now, this is fine. And let's see if this would work. What? It actually worked, but there is some validation messages. So, vacate buffer should have usage transfer DST set during creation. Okay, makes sense. So here, index buffer, but also we need vacate buffer usage flags. Transfer actually DST, because we're going to transfer to it from the staging buffer. And what else? This. Let's see now. There's only one other message here. Dot size 32 is greater than the destination buffer size 24 minus p regions 0.dsc offset. Interesting. So we got that stupid problem that we had before. Makes sense. OBS disconnected. Yeah, seems to be reconnected. Nice, lovely. So you got reconnected at this point. Amazing. Okay, so what's happening here? So basically this copy to somehow isn't doing it right. Probably because of the alignment, right? So, show, 24. So, okay. So we have two choices, either to give copy to the size, the actual size, which is this, or we could just save this size. Yeah, also I'm going to save that size to the buffer. Handle allocation. Just say size, it's actually use size or size or something. Anyway, size seems good to me. And let's just say size here. That should do the trick. Cannot find size in this scope. Okay. So info.size. And I think that's it. Or otherwise we could even save the info if you want to, but yeah, anyway. So field size is never read. Yeah, makes sense. So now let's go down to copy to. Now instead of allocation size, we gotta say dot size. I believe. And this should do the trick. Hopefully. Come on. Yeah. See now? There you go. Amazing. We have done staging. Lovely. Let's go. Very nice. Okay. So that's pretty great. Pretty great. What's next? What's next? So right now we could probably also create a UBO and start doing the matrices stuff. What else? Uniform buffers. So I'm gonna be back in a second. I'm just gonna take a, oh my god, we've been recording for 4 hours and 30 minutes. So I'm just gonna take a break, and if I can continue, we're gonna continue. Otherwise, I'm just gonna stop the live stream at that point. So just hold on, I'm gonna take a little break around 5 minutes or so. And then I'm either gonna come back and continue or just stop the stream. So see you then. Okay, hello, back. Let's go. So I think I can still go further a bit. I'd like to maybe, if possible, add MSAA. Of course, if it's not gonna take a lot of time. We're gonna see how it goes. If I can figure out real quick. Hopefully, we should be good to go. The other thing maybe is in like frame, like multiple in frame, sorry, multiple in flight frames, right? If also the same thing, if we can actually figure it out real quick, then yeah, we're gonna do it. So yeah. Is everything right? Let me make sure. Yeah, seems all good. Now, unless, well, first of all, before I forget, I guess I'd like to go to the pipeline, I think, or swap chain. Swap chain. Yeah, and the swap chain images, we basically said, I guess, current extent, right? Now, the problem with this is that there is like an exception. And that exception is the fact that in, for example, Wayland, this current extent could be not valid. Could, yeah. So in that case, you could use the window size, basically. So yeah. So I have access to window. So here's the deal. We're probably gonna be able to yeah, let's just say is equal to, so basically, how do you do ternary operators in Rust? Ternary operator or equivalence. So if else, okay, great. Let's go ahead and do it. So basically, surface capabilities. Yeah, let's do it after this. Is equal to, well, dot width or whatever. Yeah, dot width x. Basically, U32 max, I think. U32 max. I think. Please. Let me just make sure. Let me actually show you that. Surface capabilities, current extent. Vulkan. There you go. Now, as you can see, current extent is the current width and height of the surface, or the special value 0xFFFF, indicating that the surface size will be determined by the extent of a swap chain targeting the surface. Let's go. So, in that case, if this is the case, then we're essentially going. Let's see. Yeah, we're gonna give it the Windows swap chain, like Windows size, sorry. Windows size dot width. There you go. Else Windows size dot height. Oops. Height. That's basically it. Oh, what I'm doing? Hold on. No. No. Yeah, no. Hold on. So it's gonna be, so if that's the special value, then we're gonna create our own extent, essentially. Yeah, extent 2D dot, well, vacate extent. Okay. Dot width to window size dot width, and then dot height is window size dot height. That's essentially it for that one. Basically, we're going to be using the window size to determine the extent. Otherwise, we're going to be using the surface capabilities dot current extent, I think. Yeah, that's how it should be done. But of course, this should be built. There you go. We got the image extent. Though honestly, I may want to use this image extent somewhere else. Essentially, so. But for now, let's just fix this first. What else? Is there anything I'd like to fix? Let's see. Minimum image count +1. This seems great enough. Though, just for the sake of completeness, I'm gonna check the minimum image extent. Unless current extent, not this one, I mean, max image layers, current transform, supported usage flags. Yeah, that's exactly what I saw. There you go. So a value of 0 means that there is no limit on the number of images, though there may be limits related to the total amount of memory. So here's how we're going to do it. It will be at least 1. So just for the sake of correctness and completeness, here's what I'm going to do. Minimum image count +1. This with the minimum value of surface capability. Well, in fact, we don't need, so we're already using minimum image count, so there is no need for that. It's guaranteed to be that way, basically. But we do need to make sure that it's maxed out by doing surface capabilities dot maximum image count. So that could be 0. So in that case, what we're gonna do, if this guy is equal to 0, we don't need parentheses. Else that. Now, if that's the case, we're basically gonna give it max. What is it called? U32 max, or yeah, U32 max, exactly. But let me see what's happening here exactly. Oh. There you go. So minimum image count, surface capabilities dot minimum image count +1 dot minimum. If surface capabilities dot max image count is equal to 0, then we're gonna get the minimum with U32 max, which basically means it will always pick this. Else surface capabilities don't maximum image count. Too simply. Amazing, I love it. So that's basically some things for correctness. What else? Yeah, that's pretty much it, I think. Current transform, at least for now. At least for now. We could also add, currently we're using vsync, but we could in fact not use it using mailbox, but that could not be available. We should check for that. So for now, let's leave it as FIFO. And yeah, that's, I mean, let me try mailbox. Let me see how much frames I'm gonna get, how much FPS I'm going to get. That's gonna be interesting. Let's run RenderDoc real quick. And of course, to get good results, we're gonna disable the validation layers. And we're basically gonna launch application. And hold on. This is the working directory. Other than that, oops, let's check this. Explorer, go to tab of Vulkan, and let's say target, debug, build. Oops, this is it. Okay, so copy his path. There you go. And that's basically it. Now let's try to run this, see. So this is getting 185, 175 FPS, 190 FPS, something like that. Interesting. Okay, so are you sure that this is compiled? I don't think. Okay, let me try it again now. Yo, what? There you go. Yeah, we're getting 180 FPS, something like that. Okay, now let's just stop this. And what if we used FIFO instead? Let's go. Come on. Let's actually make sure to compile or build. And yeah, let's try this out. Ooh, interesting. What? I expected Mailbox to give us more. Oh no, never mind. This is, yeah, it's pretty similar actually. But I did expect Mailbox to possibly give us more frames. But anyway, so, and the frame rate is so low. It's too simply because, by the way, what happens if you use immediate mode? Just interested to see what's gonna happen. Manage application. Basically, we're not doing the, hold on. No, it's pretty much similar. Interesting. So yeah, it's basically what's limiting our frame rate right now is, what is it called? Yeah, because we're essentially using the fence and we're not starting to render the next frame before, like while presenting the other frame currently. So yeah, basically. Though we could try it out later on, but for now it's fine. So other than that, instead I'm gonna go with FIFO. FIFO is basically guaranteed to exist, to be supported basically. as long as I've imported, so that's that. Okay, so now let's try to add MSAA. So why? Too simply, so let me show you. Actually, hold on. Before that, let me just make sure to build. And yeah, let me show you. Lunch. Let me get a screen here. Oops, there you go. So I captured the frame now, and check this out. So basically, if we zoom in, you can see that we have this pixels like this. It's not smooth at all. But if we go ahead and add MSAA, which is going to take some time, but I think it should be not that bad. But basically, if we add it, we can get some smoother geometry, which is very cool. Let's go back. I mean, I know how we're going to do this, but let me just make sure that it is in our reach. So yeah, basically, instead of sampling one point in the texture, or in the, yeah, we're sampling 4 and then basically checking, or well, depends. MSAA x4 is actually that, but anyway. So setting up a RenderDoc. Yeah, pretty much we got to create an image and an image view, a transient image, which gotta be used as a, I guess, a resolve or something like that. But, yeah. So the samples should be there, and yeah, what's this? Weird. What? Oh. Oh no, this is the actual depth stencil stuff and depth image. But there you go. One. What? This doesn't make sense. Create image. This really doesn't make sense. Texture image. Like whites count to 1 bit. Create image, color format. Yeah, there we go. That's the actual thing that we need. Oh, I see. It's basically created the actual create image function and used the, okay, never mind. So yeah, we don't need this stuff, but this is the one that we need. So MSAA samples, yeah, optimal, tiling optimal, transient attachment, color attachment too, transient because, well, we don't need to store its stuff. And vk memory property device local, but it's going to be local to the device. Interesting. And then of course we created the image view, color image, format, color bit. Yeah. And then of course we add new attachment, though we don't really need all this because we're using dynamic rendering, but yeah, it's kind of close. So basically optimal MSAA samples. Oh, what? Oh, depth attachment. Oh, interesting. Depth attachment also needs to be in that samples for some reason, which is weird. Oh, in fact, all of them. Ooh. Oh my god, interesting. Interesting. And of course the resolve, right? Final layout, color attachment, optimal. Let's take care. We have changed the final layout from present to color attachment optimal. Ooh, okay, that's because multi-sample messages cannot be presented directly when you first need to resolve them. Makes sense. Oh my god, I see. So I remember I was, working with WGPU and it didn't work for me. Now I know why it didn't work, I think. And I was blaming WGPU. Interesting. Oh my god. Let's see. Samples. I'm glad I've seen this first. Lloyd OP don't care. Lloyd Sort. Oh well, this is the color attachment. Resolve. Attachment description. Defined. Attachment layout. Mm-hmm. By shader alias in MSAA always smooths out edges of geometry. Sample shading, which can improve the image quality even further, do at an additional performance cost. Enable sample shading in the pipeline, and minimum fraction for sample shading. Closer to 1 is smooth. So basically this is MSAA, but for textures, I think. Or shaders, basically. Not really. So MSAA is only for geometry, but this also for shaders, essentially. Which is pretty cool. So let's actually add this stuff. First, let's add this sample shading, because why not? Although we're not really going to see any improvement currently, because, well, we do not really have any weird stuff. Like we don't have textures or whatever. Okay. Hold on a second. Okay. So let's start by adding sample rate shading and MSAA to our pipeline. So let's go to the pipeline. Where is it? Not this one. Not this one. There you go. So let's add it to wherever. Rasterization. Well, not this. Multi-sampling. Well, I already have multi-sample. We just need to enable it. It's right here. There you go. So instead of type 1, I think we basically gotta, hold on. Let me just make sure. Let's see. By the way, did we commit what we have? Actually, we didn't. Oh my god. I'm glad I managed to remember. Okay, right now what we have added, we added the, I think, staging buffer. Yeah, staging buffer, and we fixed a swap chain creation to work on Wayland, for example. So swap chain fix and staging buffer. Okay, commit. Oops. Okay, let's start with this. And then after this, we're gonna actually go ahead and we'll try to basically implement multi-sampling pretty much. Okay, let's try to do this now. So current extend, blah, blah, blah. Let's go back to the pipeline. Okay. So how do you do it again? Just making sure. Is creating this pipeline. Hold on. Create color resources, create image. This is the color attachment. Rasterization samples. There you go. Rasterization samples. There you go. So here we basically gotta say samples. Pretty much. And let's stick down up here. Let samples to this, I think. Okay, so this is the samples, and let's just check where we actually use this. Well, nowhere? Interesting. What? Okay, great. Great. Okay, let's go. So, first thing first is we gotta create an image for that. Now, the thing that we need to watch out for here is the fact that when the swap chain gets recreated, we also need to recreate that specific image. So, yeah, we're gonna do something similar to how we have done for the swap chain and stuff like that. Do we need, no. So yeah, we need one image, I think. We may need multiple images when we have like, anyway, let's just for now, where we're doing that thing, let us say image, okay? Image equal to device dot create image. So we got a big form. Well, not too big, not as much as the what's it called, the packet, but well, okay. So the format's gonna be swap format. Hold on, this guy though, first of all be vk, well, vk image null at first. Okay, at here when we recreate the swap chain, basically, it doesn't matter in which order, honestly, but yeah, let's just do it for example here. Okay, so it's, we already have the variable here, so it's MSAA image is equal to here you go, format, swap chain format. What else? We also have extent, exact same as the extent that we have chosen where here, yeah, image extent. Interesting. So let me actually put the image extent here, I guess. Oops, I also need the surface capabilities there. Interesting. So let's grab that too. And of course, surface capabilities, current extent. What? I'm confused. Back. There you go. So basically this guy, you guys should be here. And yeah. Let's set just the extent right there. Why the formatting have failed? Weird. Cannot assign new value to immutable verb. Oh, okay. Image mutable. And mismatch types, expected image found result. Well, basically unwrap this for now. And what else? Okay, what? Expected extent 3D. Not even extent 2D. Amazing. Why in the world? Okay, let's build width, and let's give it image extent dot width and dot height, image extent dot height. And of course this allocation callbacks, which is basically none. Yeah, basically. So you could actually also build it by dereference net, which is nice. Okay, other than that, we can get these samples. Okay, samples. Interestingly, let's go back to where we have created the image, and it's right around here. It's using MSAA samples. Let's go. So, okay, not samples. Samples. What else? Got the format, the extent, the samples, the initial layout. Where is layout? Tiling optimum. I think, yeah, Vicky. Tiling. What? Interesting. What is this thing? Color attachment optimal. Oh, let's go to create image. Where is creating that? But well, anyway, let's just go with something. If in attachment optimal, maybe, I don't know. Anyways, what else? Initial layout. There's array layers. Bruh. Array layers. Sure. The image. Still 2D. Now I don't know why the stupid RustFMT is failing this. There you go. Okay. Come on. Where is it? There you go. Okay. News variable MSA image. So what's next now? Image type 2D, of course. What else? Array layers. What else? MIP levels. Oh my god, I don't know this stuff. She tells me about them pretty much. Flags, pnext, MIP levels, key family indices, and sharing mode usage also, and tiling. Ooh, tiling. VK image tiling. optimal lines. Okay, weird. Other than that, let's go with usage and share. So usage is image usage. I don't know. Maybe color attach also presents some or both. Okay, so Viki image tiling up, well, not transient and color attachment. But what about present SRC? Huh. Yeah, what about present SRC? And anyway, let's just go with this. Color attachment and the image usage flags. Probably transfer. For now, let's just go with transient as well. It's gonna be used between passes. Anyway, other than transient, so that's it for now. What's next? Next up is, let's see, I guess queue family in the season share mode. So for share mode, it's concurrent, sorry, exclusive, which is basically no need for that. The other thing is, queue family indices. Actually, okay. Other than that, well, what else? I think this is fine, maybe. Let's see. Value assigned to is never read. Maybe it is overwritten. Okay, let's try and see if this actually even works and if there's any validation layers. Yeah, let's see. Okay, we got some problems here. Actually, a lot of problems for some reason. Interesting. Extent dot depth is 0. Must be greater than 0. Map levels also must be greater than 0. Array layer, same thing. And initial layout is Viki image layout, must be undefined or initialized. Yeah, we're gonna go with undefined, why not? What else? If image type is must be 1. Okay, gotcha. So for the extent, let's go back to the extent. Dot depth is equal to 1. We have nothing. That's the first thing. Second thing is we need map levels and also array layers. Let's see what's next. And also undefined. Let's make it undefined. Where is undefined? Undefined. Where's layout? There you go. That's it. So right now the MSAA image is created. Lovely. Now of course we need to make sure that it's also the device destroy image, well, image, and fish callbacks not go. Great. Okay, what's next? So right now we got the image. Right now we also need the image view, essentially. So let's add that too. YouTube image view. Is it to vacate image? No. And now let's just create that, which is also going to be similar to what we do here. So that's something. So MSAA image, let's go. Now I'm just going to copy what we've done here. Device, create image view. So this is going to be MSAA image, of course. And of course I need to make sure to destroy the image view too. Okay. And now, what's happening here? Oh, image view here. Okay, what else? Okay, so builder image format, Swapchain format. I mean, yeah. By the way, shouldn't we actually make use of Swapchain format here, in fact? I wonder. Let me just see real quick what's gonna happen here. Oh, that's the image layout. Oh, my bad. My bad. So this should be in the file. I think, like, where's format though? Oh, it's already a swapchain format. Lovely. Okay, great. So swapchain format, view type, type 2D, yes, exactly. Aspect mask. It's probably color, yeah. So, I mean, is there anything else? That's not relevant. Okay, so that's pretty much it, I think. Duplicated code, of course. But anyways. So that's basically for the MSAA image view. We have created it at this point. She's amazing. What's next? Getting available sample counts, blah blah blah. We have created the image needed. Oh, yeah, depth stencil, never mind. Adding new attachments. Okay, so this is where things go crazy. So let's go to begin rendering, I think. Where is begin rendering? There you go, CMD begin rendering. So here we have something interesting. We have to give it the color attachments. Interesting. So how to do this? There's Swapchain image views, Lloyd OP, store OP. Okay, let's see what exactly they've done here. Final layout samples. So attachment to interesting. Color attachment resolver. Okay. Color attachment optimal. Lloyd OP don't care, store OP don't care, because we really don't care about that once we were done with it. In define, oh yeah, there you go, present as our CKHR, interesting. Oh, well, in fact, we probably gotta do it ourselves there, yeah. We gotta actually transition the image layout of that too. So that's interesting, but that's pretty easy, I think. Okay. So basically, I think what I'm gonna do is, now instead of from ref, we're gonna make use of a slice. And for that, we shouldn't use, we should build this thing by basically, and instead of from ref, we're gonna use basically to making this work. To actually do something similar to this. Yeah, pretty much. And basically, what we're gonna make sure is, so instead of Swapchain image views, we're gonna go with MSAA image. The other thing is Lloyd OP don't care. Same thing with you don't want to store it really. It's just gonna be displayed. And then the clear value, and we don't need clear value because we're not. And then the image layout, it's in the find, I think. Actually, hold on, no. I'm not sure. It's like, not sure exactly. Hold on. Rendering attachments, it's, I guess color attachment optimal, yeah, probably. So yeah, that's it for that one, I think. And we also gotta add something else at this point, which is, so there's stencil, color attachment, view mask, pnext, is type, render area, layer count, flags, and resolve. Well, where is what? Okay, where's resolve? Oh, there you go. So I could say resolve image view, resolve even image layout, resolve mode. So what's it's doing here? Color attachment, resolve ref, layout, color attachment optimal, final layout, find present source, final. Subpass.p resolve attachments is equal to color attachment resolve ref. Interesting. Color attachment resolve reference. That's for the whole subpass. But in my case, should I put the resolve here or there? Not sure. Max, none from raw, average, average KHR. Not sure what's that. There's even none KHR. Sample 0. Not really sure that. Let us things out and see what works, I guess. Anyway. Resolve image layout. That's gonna be basically, where is that layout? There you go. Probably this with IDK. What else? Resolve image layout. Okay. What else in terms of resolve? There is resolve image layout, resolve mode. I don't know about resolve mode yet. Anyway, and resolve image view. No, I need to actually check this out. Hold on. Rendering attachment info. Let's go to the Vulkan. Actually, not this one. Rendering attachment info. VK rendering attachment info. There you go. Let's go. So, image view is the image view that will be used for rendering. Will be enduring rendering. And resolve mode is the final data written into image view or be resolved into resolve image view. Into resolve image view. Interesting. This is another level. Is an image view used to write resolve data at the end of rendering. Is an image view used to write resolve data at the end of the rendering. Resolve image layout will be in during rendering. Okay, great. I see. Values in image view are loaded or stored according to the values load OP. Then resolve oh my god, no. Resolve mode. Okay, it's not. Suspending bit. Interesting. This is interesting. Multi-sampling, okay. Add a new attachment. Modify, update color depth, construct. Oh, interesting. They added MSAA samples there. In the depth attachment and the color attachment. Alright. Final layout, current, okay. I see what's happening here. It's interesting. So basically, where is samples in this attachment? There's no samples. Amazing. I'm confused. Okay, hold on. One, two, three, four. Okay. 1, 2, 3, 4. Count one bit. 1, 2, 3, 4. Okay. Great. So in Vulkan, depth resources, clean up Swapchain, add new attachments, samples, creation info structs. So we need to somehow add samples into the attachments, but we do not have that with dynamic rendering, which is crazy. And then here what we have. Notice that we have changed the final layout from this is because it cannot be presented directly. We first need to resolve them to a regular image. Okay, that's because multi-sampled images cannot be presented directly. Do you think Rust is better than C++? And hello RendMFS, welcome to the live stream. You think Rust is better than C++? Yeah, pretty sure it's better. But the problem with Rust is the borrow checker can be annoying and it doesn't allow you to be so adventurous. And it's kind of constraining, and also about safety. So like the borrow checker has some safety guarantees that you have to uphold in safe code. Now, if you break those guarantees, then everything becomes crazy in safe code. But otherwise, I think Rust is much better than C++. And that's understandable because, well, C++ have a lot of tech depth in that it have to account for. Like basically you have to keep the compatibility with C kind of, and also you have to keep compatibility with older C++ standards and all sorts of weird stuff. While Rust, it's a new language, you have made a lot of good choices from the get-go, basically. So that's why it's basically a better language, pretty much. And by the way, in fact, C++ is actually kind of like getting into an evolution to be like Rust in some sense. Like for example, the what they're called? No, hold on. Like span, for example. Span is just a Rust slice. There is other thing too. We call them iterators in Rust. I think they're called views. Yeah, they're called views and ranges in C++. We already have that in Rust. It's called iterators. And yeah, there's a like also option like Rust had an option already, while C++ have just added that too. And yeah, a lot of stuff like this. So basically, TLDR, I think Rust is much better than C++, pretty much. But there's still reasons why to choose C++ for very unsafe code, maybe, although you could probably get away with Rust in safe, but it's Rust in safe is kind of icky. But either way, you can do that with Rust in safe. And also another thing is, yeah, the ecosystem. It can be a little hard to actually use libraries that are created in C++. There's just a lot of libraries out there, and if you want to use it, you have to create a binding. You have to make a binding library for it or something, or otherwise find it in the library. But other than this, pretty much Rust I think is the best. Thank you for replying. Also, I'm currently focusing in Lua Roblox, and good luck. Have a great day. Thank you for coming in. Thank you for asking the question. Have a great day. Count 1 bit. Lloyd OP don't care. Lloyd OP store. OP store cannot be presented directly. We first need to resolve them to a regular image. This requirement does not apply to the depth buffer since it won't be presented at any point. Therefore, we have to add only one new attachment for color, which is called resolve attachment. Has to be instructed to resolve multi-sampled color image into a regular attachment. Create a new attachment that will point to the color buffer. Shall resolve as the resolve target. To the color buffer. Set the Next, update render path infrastructure with the new color attachment. So there's color attachment, depth attachment, and then color attachment resolve. Okay, color attachment resolve. Interesting. And that resolve is what is taking this attachment equal to 2. Interesting. I really need to see this exact code in actual entirety instead of this jigsaw puzzle. But anyway, swap. Oh, okay, let's go. All right, I see. So attachments. So the first attachment is color image view, and then Swapchain image views. What? Hold on, color image view? Really? Hold on. Color. Destroy image view is equal create image view color image color format aspect color bit 1. It's basically color image. And what is color image? Okay, let's see. Create image. transient. Oh, right, I see. Usage color attachment bit, transient. Okay, I see now what's happening, kind of, to some degree. So basically, the first attachment would be the MSAA sample stuff. Then the second attachment in my case would be the actual Swapchain image view. Okay, so that means actually basically do this first. There you go. So the MSAA image view first. Don't care. Color attachment optimal. Then color attachment optimal here. And then we're basically going to tell it to resolve. Resolve image view. And I think it resolves into the Swapchain image. Basically. Rendering here. In the MSAA image view, essentially, yeah. So don't care, color attachment optimal, let's go. Do you have any suggestions for me? Because I get lazy when coding something. I do have things in mind, but it just makes me more lazy. First of all, I think you probably have to focus on one thing, because the more thoughts and like ideas that you have in mind, the slower, like the lazier you'll get, because you just have a lot of choices, a lot of ideas that you just cannot pick one. So you have to make sure to focus on one thing at a time. That's the first thing, I guess. And also, it just makes me more lazy. Because I get lazy when coding something. Like, why do you get lazy exactly? That's the thing. Like, are you a hobbyist, a programmer hobbyist, or not, or what exactly? Like, give me more details. Resolve image view. So you're gonna resolve into the Swapchain image, and this is basically what we're gonna use to actually render. Okay. Now we should make sure to add resolve. Resolve mode. Otherwise it won't work. So resolve. Can just use flags. Yeah, seems like. Okay, so there's here max, there is average, none. Weird. Resolve mode. Okay, I see. Gotcha. Let's just go to average. Yeah, that's one thing that we need here. But I see what's happening there. For example, I started using camel case, but a few hours passed. I prefer past case, and it's just stuck in there. I started using camel case, a few hours passed. I prefer. I don't know exactly what to say about that. I mean, just keep on going with that. I mean, I don't know. Average. So basically, here what's happening. I just realized what that's about, because I think this is new. This wasn't a thing in when it comes to render passes. I think this is new to with dynamic rendering. Basically, if you go back here, so essentially, samples per pixel. Yeah, we have this 4 dots, this 4 samples per sample, or whatever you want to call it. So basically what you do want to do, in this case it seems like average. Why? Because, well, 1 divided by 4 plus, well, 0.25 plus 0.25 divided by 2 gives you 0.25. So what? Hold on. So like, what is the average here? So like 2 out of 4. Hold on, what? No. Actually, kind of not understanding. Hold on. Average, max. Actually, not really. I'm not sure. Like micro optimizing something that is basically necessary since it's only a minor microseconds difference. Also, for the naming conventions that I mean above is about variable function names. Well, welcome to the club. That's basically what programmers face every day. The hardest thing is naming stuff, naming functions and naming verbs, etc. And also the other thing is trying as much as possible to avoid micro optimizations, like to avoid the, I don't know what to call it, the irritation to go ahead and try to do like the craziest optimizations possible. And also the other irritation, which is to what is it, to, yeah, to make abstractions instead of just writing code. So as you can see here, my code, everything, almost everything is in the main function. Like almost everything is written in the main function. Never ever start with objects and functions all around. Like, just do the code, just make it work. And only abstract things when it really makes sense. Like, for example, here I only added this buffer. Why? Because I'm having multiple buffers. But for other stuff, I didn't, because I just have one thing of it or two, or it doesn't matter. But for buffers, I know for a fact that I'm gonna have like a lot of buffers. So I just gone ahead and at this point just abstracted the code into its own kind of class and create these methods into it. But other than that, I don't even bother, unless if it's something really small and it would make it more readable. Like for example, this vertex struct and push constants, which made it much more readable and intuitive on what's going on. But yeah, as you can see, it's like avoid abstraction, avoid micro optimizations, and just write the code. Avoid all that paradigm stuff and OOP, object oriented programming, all that crazy stupid stuff. Just avoid them. Only use them when you really, really need to. And after you make it work, like even like for example, buffer, I knew that I probably would need to abstract it away, but I didn't. First, I just written the code directly in line. I even copied and pasted the code just like that to create multiple objects. But at some point, it just became unmanageable that I just had, like I was forced to actually go ahead and abstract. And I'm glad it turned out great. The abstraction is also great, pretty much, because I know what I need beforehand. I have multiple buffers and I can see what is common between them and what is not common between them. So it's also ended up with a better abstraction, basically. And so that's pretty much it. For naming, I don't really have anything, maybe naming conventions. Try to just adopt some naming conventions and stick to it, basically. And the best naming convention that you would stick to, look for your community. Look for, like, for example, if you're programming in Lua, look for what people are mostly programming in Lua, what naming conventions they use, and just use that. Unless if something really doesn't you like, then just change it. But basically, make sure to have some fallback naming convention that everyone uses. For example, like if you want Lua naming convention, Roblox Lua naming convention, just check it out. Go ahead, and this would basically, at least as much as possible, go ahead and get that mental struggle that you have to go through for naming every single thing. For example, here, as you can see, Roblox Lua have a style guide. And here it tells you a lot of stuff like the purpose of a style guide is to avoid arguments. There's no right answer to how to format code, but consistency is important, so we agree to accept this one. Somewhat arbitrary standards so we can spend more time writing code and less time arguing about formatting details in the review. Also, when someone new joins in your team, for example, or you join some other team, and you're mostly gonna find them using that official, or at least most commonly used style guide. So you won't have any trouble there. Avoid magic such as surprising or dangerous Lua features. Optimize code for reading, not writing. And be consistent with idiomatic Lua when appropriate. So just read through this. For example, if you're working with Roblox Lua, read through this and just adopt it pretty much. There you go. It's also telling you what's good, what is bad, for example. It's not objectively bad or good, but that's the standard basically. And just adopt this. It's like it will really take away like the least choices you have and that you make available for yourself, the more focused you are on the task, essentially. And that's basically it. Like I actually suffered from such problems a lot, and in fact I'm still suffering from them, but it's became manageable, especially the fact to avoid abstractions. Just write code, write the whole thing in one function, who cares? And then when you actually need to abstract stuff, go ahead and abstract it, pretty much. And I think also a lot of other programmers have the same, or at least came into the same conclusion. Don't abstract stuff too early, or don't try to get it perfect the first time. Just write code that works. Then when it becomes a problem, then go ahead and solve the problem. That's essentially it, I think. That's pretty much my advice for that. Hopefully that was understandable. So yeah, pretty much. Okay, so I forgot completely where I was at this point. Okay. I don't know. Heyo, Dijik, welcome back. Heyo. Is Zig good? Zig programming language. Zig is pretty good. In fact, much better than Rust. But when it comes to low-level development, for example, Vulkan, I render like Vulkan render, I would go with Zig. Go, I don't really, I didn't really go seriously. Like haven't tried it seriously yet, the Go programming language, because I just didn't have any reason to. It wasn't really getting something new there. Yeah, it's like Go. I can't really give like an unbiased opinion about it. But for Zig and Rust, I love really much these two languages. They're pretty much my most favorite languages. Though Zig is still new, I still have a long way to go to actually become good enough. But once it at least released, I'll probably pick it over Rust for low-level languages like this, of writing a renderer, like a Vulkan renderer. I would surely go ahead and use Zig. But for the higher level languages, well, not higher level, but mid-level kind of thing, like for example, game engine, or not really game engine. I don't know, not sure, but mid-level, like low level, I would go with Zig. Mid-level, I would go with Rust. High level, probably gonna go with C#, pretty much. That's currently my languages, but of course that could change. A lot of like my favorites have changed, but currently this seems to be the case. So Zig for very low level stuff like creating a render, Rust mid level, C# high level. That's basically my choices currently. So yeah, pretty much. Okay, so I will learn. Yeah, better focus on one thing. Learn Go. Nice. You learn Zig and Rust and learn Go and something else. Yeah, pretty much Zig and Rust. I think they're pretty much going to be like the future languages. So yeah. Uh, so but currently Zig is kind of lacking, especially when it comes to the LSP, like the language server, like basically like autocomplete and stuff. Very lacking there. Rust Analyzer is basically the best you can find when it comes to LSPs. And the other thing is the build system. Same thing. The best build system, in my opinion, currently is Rust build system. It's just very easy. You just go ahead, cargo add this library, and there you go. Boom. Also, every library have its own documentation with the same style. It's just very great. Like Rust is pretty much the best. The only thing that is very annoying about Rust is managing like the borrow checker can be quite annoying, frustrating when you really want to handle and save things and stuff. That's the only thing I believe. And also the fact that Rust doesn't give you explicit, like isn't very explicit about allocations, like where allocations happens, etc., and what allocator to use. There's like just one global allocator. And in fact, all languages like this, or at least most languages like this, while Zig is actually very explicit about which allocator and when do you allocate. Like there's no global allocator. Every time something needs to allocate, it will ask you for an allocator. I very much love that about Zig. In fact, before learning Zig, I never even knew that much about allocators, but after checking out Zig, it just makes sense. So, but I understand that it becomes quite tedious because every time you have to actually give it an allocator. But honestly, to me, I'd like that such a thing in Rust. Though it is possible, but it's kind of clunky in Rust, pretty much. So yeah, that's basically it when it comes to languages, at least currently. Of course, this would change. Maybe it would change with time. So yeah, that's pretty much it. Okay, where I was, color attachments, and there's builder. So we have the MSAA image view. This is basically, yeah, this is basically where we're gonna render to. Okay, where we're gonna render to, and where we're gonna resolve. We're gonna resolve into this guy right here, the actual Swapchain image. Hmm. Though I wonder if we really need to clear the image at this point, because well, we're gonna be writing this whole image. We're gonna resolve it into this guy. So maybe it's not needed anymore. But in fact, Lord Judgment, Lloyd OPs don't care. Interesting. Hmm. Hold on. Get an available sample count. So let me try to figure this out. The problem right now that I have here is the fact that this tutorial is basically using render passes, but I'm using dynamic rendering, which is the new uh, technology, I guess, that you should use with the Vulkan. But yeah, anyways. So let me see. Multi-sampling rasterization. So basically the first attachment is the color imagery, which is the MSAA. Okay. Second is the depth, and the third, well, we don't have depth currently. The third is the actual Swapchain image. Color attachment resolve. Okay. So this what goes into the Swapchain image view. Interesting. Color attachment resolve. There you go. This one. Oh, what? Really? I'm kind of confused now. Yeah, this is the one that would be presented. But why store OP doesn't care? But anyway, let's just try it out. So we're gonna go with for the second one, it's gonna be don't care, don't care. Hold on, hold on. I'm actually seeing the wrong thing. Hold on. Yeah, I'm seeing the wrong thing. Yeah, go back. Oops, what I've done. Okay. Okay, I see. So I was actually looking into the wrong thing, which is stencil, which is irrelevant here. I need to check this guy. So it's Lloyd OP don't care, but it's actually store OP. Yeah, this is what I was thinking. Yeah, it would be Lloyd OP. So we do want what? He Lloyd OP don't care. Yeah, that makes sense. That makes sense. That makes sense. Color OP don't care. Because we don't need to clear because, well, the whole image will be resolved. So anything that is in the actual image will be just replaced. So there's no need to actually clear it, I think. So what we gonna do now? All right, let's see. Makes sense. So here we're creating the image view. Nice. Nice, nice, nice. Where we're beginning rendering. There you go. Here. Okay, let's see what we're gonna do exactly. So here I think don't care, right? Is it? I mean, hold on, it's pretty simple actually. So this final thing, which is color attachment resolve, let's see what it is about. There we go. So this one, the final thing would be the Swapchain image format, which is indeed the case. Then we got the count 1-bit. This is not here. Okay, Lloyd OP don't care and OP store. OP don't care. OP store. So that's correct. Okay, we don't want to clear it. There's no need. And this we want to store it. Here, clear value, default, color attachment optimal. We don't need this guy. That's basically it for that one. Okay. Okay. Then resolve image view. We want to resolve it to this guy, which is the Swapchain image. Great. Resolve image layout, color attachment optimal. Nice. Image layout. Great. Okay, now what about this? Lloyd OP. I would guess this is gonna be clear. For sure, I think. And store OP, I'm not sure. I guess don't care. But I may be wrong. I'd very much like to find the code to this whole thing, not just one fragment after the other. Just annoying. Okay, let me see if I can find it here. Oh, okay, let's go. Let's go. Now I'm gonna get it. So multi-sampling. Okay, let's load up our web editor. And let's see. Okay, great. PKHR Swapchain extension name, blah blah blah. Let's go to image color attachment. There you go. There we go. There we go. Okay, so we have color attachment, depth attachment, and color attachment resolve. Amazing. That's what I wanted. Okay, there you go. So load OP clear, and then store OP store. That's the first thing. So these two things would be clear and store. Great. What's next? Don't care, and defined. Not sure of this one, but anyways. What else? There's also this clear. Oh, why this is clear? That's ridiculous. Oh, this is depth attachment, makes sense. Color attachment resolve. This would be don't care, store. Makes sense. So don't care, store. So clear, store, don't care, store. Makes sense, makes total sense. Okay, nice. Now what's next? Pipeline bind point, blah, 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 blah. Yep, let's just try this out and see what validation would tell us. And yeah, I'm gonna be rendering to this guy. And now the swap chain image views, what this would happen to it. So here we have it. And honestly, let us actually refactor this. I guess introduce a variable, replace all with numbers. IDE error occurred. What? Now I have no idea what it did. Clear store, don't care store. Go back. Lloyd store. Don't care. In the here store. Store clear. Okay. Clear store, don't care store. Cool. Cool. So, okay, let's see what we have here. So basically, pipeline barrier 2. Now this swap chain image, the old layout is undefined. Okay. This one is attachment optimal. Well, that's not going to be the case anymore, I think. Is it? I mean, it's pretty simple actually. Just check out here. So initial layout is undefined. The final layout is color attachment optimal. And this one final layout is present as our CKHR. But we're going to present SRC. So we don't need to actually, yeah, I'm kind of going crazy right now. But here's the deal. I think I'm just gonna follow my logic for now. And we don't need this anymore, I think. SRC stagebacks ask. Actually, we do. I mean, where's the initial layout? Undefined. Where it sets the layout again. Gee, let me check all the layouts. There you go. So we do actually need that. So yeah, both of them would be optimal at first. Yeah, okay, right now that makes sense. So basically I'm just gonna copy this. It's gonna be color attachment optimal. So let's just copy this guy. And let's see what we need to change here. So instead of this, we're going to say MSAA image. The other thing is attachment optimal. Why does this have attachment? Oh, I'm in the wrong spot. Hold on. I'm in the wrong spot, not here. Let's go back in the start. Around acquire next image command bar. There you go. So here we're basically going to transition the image. Which image we're going to transition the MSAA, the multi-sampling image. So from undefined to attachment optimal. Color attachment right. Oh, well, I have to care about this excess mask stuff. It's... Well, that's gonna get crazy. Pipeline stage flags, top of pipe, color attachment output. Average. Image views, Swapchain image views. Image view, okay. I guess let's just try this out and see. Yeah, I guess so. Let's try. There you go, we have a problem. Let's see where that problem is. Oh my. I forgot to actually bind memory for the image. Well, that's great. Well, okay, let's actually create a memory for the image too, just like we did with the buffer. So something similar to this, I think. Memory requirements, create buffer, handle. Yeah, something similar to this, very similar in fact. Memory requirements, bind buffer memory. Okay, let's grab these and let's go down where we're creating the image. So after creating the image here, say memory and memory requirements, I think. Maybe, let's see. And the handle is basically, well, I'm gonna say image. And about the allocator, it's gonna allocate. The name is, well, and then memory requirements, and then the location is, well, yeah, memory location. And this will live in the GPU only, I think. Yeah. Linear true allocation scheme. This is as fine as managed, I think. There you go. The other thing is, instead of bind buffer memory, we're going to bind image memory. And we're going to combine the MSAA image allocation to the new allocation. It's basically pretty similar to the way we do it with buffers. In accessory and save block, okay, remove it. And that's hopefully it. Same thing here. Makes sense, I guess. Let's see what's next. So I believe right now we have gave it some memory. Ooh, okay, it seems to be working out, though we got some warnings. In fact, a lot of them. Okay, let's see. So, image view, this crazy image view, must not have a vk sample count 1 bit. Yo, yeah, it's finally have panicked right now. Let's actually stop this. Must not have a vk sample count 1 bit. Resolve mode is average bit. If image view is not equal to vk true, what? If image view is not vk null handle, resolve mode is not, and the pnex chain does not include the vk mode. With the multi-sampler signal. Okay, interesting. So we have this problem in begin rendering. Let's go down, begin rendering. So it's basically telling me that one of these guys have the wrong image samples basically. So must not have vk sample count 1 bit when resolve mode is vk resolve mode average bits. What is the other thing? Currently bound pipeline must be equal to color attachment count to the current render pass. Gone with vk. Currently bound graphics must have been created with equal to color attachment count. Oh, so the pipeline too. We gotta actually edit the pipeline attachment stuff too, I think. Hold on, makes sense. So where we're creating the pipeline? Well, somewhere around here. Let's see. Let's see. There you go. This is probably it. Color attachment formats. Let's go. So we need to give it the formats. Well, it's basically Swapchain format, but 2 times. So let's go ahead and do this. Because both are the same format, essentially. So there you go, color attachment formats. Is there anything else that I haven't checked up on? There's view math, color attachment count. This okay, must not have one. Okay, let's try this now so we can see if that have removed some warnings at least. Okay, stop it. Okay. Color attachment counts must. Oh, okay. So there's a lot of crazy stuff. Interesting. So where color blend state attachment? Color blend state. Where is that? There you go. Attachments. So we also need to do this. Okay, great. Let's grab this guy and let's make. Let's do it basically. Though it's probably a builder. Yep. So let's just dereference this itself. And yeah, it's pretty much similar. Same thing, in fact. But is there anything else that I need? That's all good. What else? Okay, stop it. So yeah, right now we just have this problem of sample counts. So, okay, let's go down to where we have that stuff. What is it called? Yeah, begin rendering. And right now we just have to mess with this, I guess. Oh, actually, yeah, basically, I guess maybe we're good enough. but maybe it can't be resolved type 1. Try, for example. If this works, oh my god, that would be great. Well, it works, but we have some problems. Color attachment reference 1 has sample count 1 bit, whereas first use color attachment ref has sample count 2. The Vulkan spec states if none of the blah 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 image view members of depth attachments blah 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 have agreed to the same sample count. Weird. Okay, what else? Currently bound pipeline is created without a VK sample count info structure. Currently bound graphics pipeline. Color attachment ref1 has sample count VK sample count 1 bit, whereas first use color attachment ref has sample count 2. What? Okay, maybe I know what's happening here. Let's see. Let's just try stuff up. Begin rendering. Okay, let's see. So the image view is MSAA image view. Swapchain. Well, I honestly don't know. Can we find some rendering, some dynamic rendering in MSAA? Okay, what is help understanding? Vulkan, of course. So yeah, there's probably no examples of this. Walaikum assalam, oh GG Kieran, welcome to the live stream. How's it going? Multi-sampling, setting up a render target. Pretty weird. There's no examples out there. Color attachment ref1 has sample count 1 bit. It's basically talking about the second one. Whereas first used color attachment ref has sample count 2. Vulkan spec states that if none of the VK AMD mixed attachment samples extension or the multi-sample render to single sampled feature enabled, image view members of P depth attachment, stencil, and elements of color attachments that are not VK null handle must have been created with the same sample count. Well, I don't have control over Swapchain image view. What? Okay, what is the second one? If the currently bound pipeline was created without a VK attachment sample count info AMD or NV, and multi-sampled render to single sampled feature is not enabled, multi-sampled render to single sampled. Features not enabled. The current render passing system was begun with the color attachment count parameter greater than 0, then each element of the vacate color attachment array must have been created simple count equal to the value first rendered for the currently bound. Color attachments array. Okay, here's the deal. What if Swapchain image views, let's see. What if we set the samples here to 2 or something? What? We don't have samples here? Okay, so you cannot really do that with image view. And I swap image. Oh, hold on, what? Let's go to create swap chain. Okay, here. Is there like samples here? Okay. No samples. So we have samples. Let's see. I literally have no idea how this works. There's like literally no example out there for how to make multi-sampling work with uh, dynamic rendering. So that's crazy. Well. Okay, go back to begin rendering. Let me try even more. That is another level. Do you guys have any suggestions on how to fix this? Image view. What if I've done... If I grab this instead and used MSAA image view here instead. No idea. Yeah, it doesn't even work now. Interesting. So we have okay, so at least with the current setup, it actually kind of works. I mean, is MSAA really being done right now, by the way? Hold on. Let me check it out. Let's actually run this with RenderDoc. So as you can see, here's the result without MSAA. Let's hope and see if that works now. Launch. Fine, why not? Actually, never mind. Just no. Ooh. Okay, hold on. Let me actually build this first. And let's launch it. Let's see if MSAA is actually working. If that's the case, I'm gonna go crazy. So, nope, it doesn't. Yep, it doesn't. And that's another level. Ooh, this actually may help us see what's going on. So we have a 2D color attachment. We have a Swapchain image and another Swapchain image for some reason as the outputs and the inputs here. Two-D color attachment, Swapchain image. Swapchain image, okay. So what happens here? What? Like all of them gets rendered? What? This doesn't make any sense. Is it? Destination. What about these? Ooh, okay, hold on a second. I'm seeing something very interesting here. Look at this. I think we may have, we're having MSAA, but we're having them in the Swapchain images. Multi-sampling, that's MSAA. We're actually having them in in the Swapchain images somehow. Oh, but why did... What? Hold on. I'm very confused. I think it actually works. What? Hold on. It's very noticeable with MSAA X8. Yes, it works. Of course, it panics at some point. But I think it does indeed work. Let me make it even crazier. 16. I wonder if I do support 60. I don't think it has 64. Let's go with 32. I wonder if my GPU supports. Let's see. Okay. That should be very visible. Really don't know. I don't know. What if I set multi-sampling 1? Come on. No, it doesn't look... I don't know. Let's build this. And let's check this out again. Try to run it. Capture. Oops. Yeah, there you go. Ooh, GPU device loss. Okay, okay. Yo, what happened? What? Let me launch the application again. Capture it. Interesting, it just doesn't work. What do you even mean VKR initialization failed? What? Really, this doesn't make any sense. Well, I think honestly that's it for now. Probably. I'm gonna try to research more on this, why it doesn't work, and if there's any updates, I'm going to tell you in Discord. Please make sure to join Discord. And yeah, that was it for this live stream, and see you later. Goodbye, everyone.
Bye.